Hello everyone, we are the two-wheeled obstacle avoidance robot team. We are sponsored by Raytheon. Our Raytheon liaison is Dr. John T. Jacobs. Our faculty advisor is Bob Dempster. Our group members are Eric Lamb, Byron Lara, Andrew Fernandez, Brandon Tomka, and Orlando Garcia, and we are located at the California State University of Los Angeles. My name is Eric Lamb. I am the team lead as well as the main programmer for the PSOC 6 microcontroller, and my focus is implementing and integrating the algorithm for obstacle avoidance.
My name is Byron Lara, and my responsibility will be to create an algorithm for obstacle avoidance and wireless controller.
My name is Andrew Fernandez, and I build and test the electrical circuit for the obstacle avoidance.
Hi, my name is Orlando Garcia, and I'm the main programmer for the Arduino wireless controller, and my focus is on implementing and integrating the algorithm.
And my name is Brandon Tomka, and I'm responsible for building and testing the electrical circuit for the wireless controller.
I will now move on with the project introduction. So this is an ongoing project. The objective for this year is to make the robot balance while avoiding obstacles and to have a wireless controller move the robot. The self-balancing robot is designed as an inverted pendulum on two wheels. Figure 1 shows a regular pendulum. It consists of 3 sections, a pivot, an arm, and a bob, or a center of mass. Figure 2 shows an inverted pendulum. Similarly to a regular pendulum, it consists of 3 sections, a pivot, an arm, and a center of mass. However, in order to be an inverted pendulum, the center of mass must be above the pivot point. Our robot shows the inverted pendulum property because the pivot point, which is our axle of the wheels, is below the center of mass. The scope of our project is that we will field the self-balancing robot from last year, design and implement a wireless controller for the robot, replacing the wired interface from last year's robot, and maintain balance while avoiding obstacles. The requirements we were provided by our client were that the robot shall maintain balance on 2 wheels, detect and avoid obstacles more than 38 centimeters away, and be controlled wirelessly by the user. The requirements we derived from the client's requirements were that the robot shall balance for at least 15 minutes, be controlled using a radio frequency module, and detect and avoid obstacles within 38 centimeters. I will now pass it on to Byron Lara with the project overview.
Thank you, Eric. So this is last year's design. So a couple of things to note here is that they had 3 main platforms. So they had the bottom platform here, which is considered our pivot point, as Eric mentioned, on the inverted pendulum. Our pivot point is going to have our 2 motors, or then our 2 wheels, as well as a battery and the platform itself, which is a wood piece. And then we're going to have our second platform, which is a middle platform. And that's going to be our PSOC 6 on it, which is our microcontroller, a shield with our IMU on top of it, and 3 ultrasonic sensors. And then finally on top is going to be our top platform, which is going to have our motor drivers and our RF module. And then the right picture, something to know here is this: you can see how the wiring kind of looks. It's kind of cluttered, and it's a lot of the wires came loose during a lot of our debugging section. Another thing to note here is that there's 2 buck converters with the blue light on them. So those blue lights helped us as indicators to make sure that the robot was getting the proper power. So anytime those lights came off for us, they would start flickering, and then they would turn off, and that showed us that we needed more power on the robot and that the battery needed to be recharged. So this is how we changed our robot design up a little bit. So we changed it to have only 2 platforms, and we also added a PCB, or a printed circuit board. Basically, this helped us to limit the number of wires needed. As you can see here, we didn't limit all the wires because some of the components weren't mounted onto the shield, so we needed to bring the wires out. But we did limit the number of wires, making it easier for us to debug. And as I mentioned, the printed circuit board was created to limit the wiring. So, so we did have some restrictions when we were creating this. One of the restrictions was that we wanted to make sure how many layers it could be when we created it. So we had options between 1 to 3 layers. So 1 layer wasn't enough because we had a lot of wiring that needed to be done. And as you can see here, the picture to the right shows a green wire and a red wire, which are the 2 different layers. So a lot of the times they're intersecting. So if we had only 1 layer, a lot of these wires would be intersecting, and there was no way to get rid of that. So we made sure to go with 2 layers. We could have gone with 3 layers and made it more, made all the wiring fit, but the difference in cost was $15 between 3 layers and 1 layer. So the 2 layers was $10 versus 3 layers being $25. So we wanted to be very cost efficient with our design. So we went with 2 layers, and then we just soldered some of the rest of the pieces on. Another restriction was, as I mentioned earlier, was that not every component could fit on the shield. So the RF module or the radio frequency module and the ultrasonic sensor couldn't fit on the shield because of the either design or because the RF module had some interference with the board. So we had to place them outside. So if you notice, there's some holes on the bottom, and on the top there's a little bit of holes. Those holes are created to make header pins, which would then come out of the shield and connect to the proper components on the robot. The second thing that we made as an improvement was that our mechanical design was different. So originally we had a robot that was 20 centimeters in height. So that 20 centimeters in height, and then it had 3 platforms. And then we shrunk it down to only 2 platforms, and it was 6 centimeters in height. This isn't the overall height, it is the height from the first platform. So not including the wheels and the motors, because we're considering all that as one pivot point. And so by reducing the height, we actually were able to reduce the mass moment of inertia by 250%. So this is a big improvement, because by decreasing the mass moment of inertia, we were able to decrease the torque needed to rebalance the robot when it was imbalanced. So if you look to the right over here, the torque is equal to I alpha, which is the moment of inertia, times the angular acceleration. So by decreasing the moment of inertia, we were able to decrease the torque needed to rebalance the wheels. This is our system architecture. So as I mentioned earlier, we had a lot of components on the robot, including the ultrasonic sensors, IMU, and the RF module. And all of those sensors created sensor outputs, which were then inputs for our functions, which were our angle calculation, balancing, RF receiving, RF controlled motion, obstacle detection, and obstacle avoidance. And of those functions, balancing, RF controlled motion, and obstacle avoidance created outputs, which were then used as inputs for our motor driver, which would then create robot motion functions, which would then tell the robot how to move for each different function to accomplish its proper task. So for example, if we needed to balance, the balancing function output would help the robot move in the direction and magnitude that it needed to rebalance the robot. And this is our software flowchart. This is an overview of how our software works all together with each other. So we have 3 different inputs. We have the balancing, the wireless, and the obstacle avoidance. So we start off with our balancing because that's our most important function. So we want to make sure that the robot's always balanced at all times. So we check our angle calculation, then we go into checking if it's greater than 4. If it's not, then we go straight to the receiving RF data. And if it is, we'll balance, and then we'll go to receive RF data. And then from there, it checks if there is any RF data being received. If there isn't, we'll go to the obstacle detection. And if there is, we'll move the robot and then check if there's an obstacle. And then once again, if there is an obstacle, we want to make sure that we are able to avoid that obstacle. And if there isn't an obstacle, we'll rebalance the robot to make sure that it's still balancing properly. And this is an electrical block diagram showing how our different electronic components are connected to each other. So on the physical robot, we have our main microcontroller, which is our PSOC6. On that PSOC6, we're going to have the battery, which provides 3.3 volts to the microcontroller. This is done by using a buck converter to buck down the voltage of the battery from 12 volts to 3.3 volts. And then we have our inertial measurement unit. This helps us to determine the offset angle from our vertical, from our desired vertical. We also have these 2 motor drivers and 2 stepper motors. And then we have 5 total ultrasonic sensors. We have 3 in the front and 2 on each side, 1 on each side, which is the left and the right side. And those 2 are used to determine whether or not the obstacle has been fully cleared when we're in obstacle avoidance phase. So while it is avoiding obstacles, we want to make sure it has completely avoided the obstacle before we move on to the next step. In our blue box here, we have the remote controller. The remote controller consists of a thumbstick, which is the remote controller itself. We have the secondary microcontroller, which is the Arduino Nano. And then we have the RF transmitter, which is going to be communicating with the RF receiver wirelessly, which then will set from the RF receiver will send data to the main microcontroller and to the motors to move the robot. And I will be passing it to Andrew Fernandez for balancing.
Thank you, Byron. Now we'll be talking about the PID controller. PID stands for proportional, integral, and derivative. A PID is a feedback control loop that calculates the error between the desired orientation and the measured orientation that we want from the IMU. In the figure to the right represents our feedback loop, which consists of our PID controller, plant, aka robot, and sensor block. The PID controller has three variables: proportional, based on the current error; integral, which accumulates the previous error; and derivative, which predicts future error based on current rate of change. Then sums all three variables to find the controller output that the plant. Like I stated in the previous slide, there is a sensor block within our. In that sensor block, there is an IMU and an alpha filter. An IMU is an inertial measurement unit that consists of two sensors, a gyroscope and an accelerometer. A gyroscope measures the angle velocities for roll, pitch, and yaw. Accelerometer measures the acceleration in the x, y, and z direction. An alpha filter, which consists of two filters, high pass and low pass. A gyroscope is then goes into the high pass filter, which then attenuates to the low frequencies, as the accelerometer goes into the low pass filter and attenuates the high frequencies. Next slide. Here we have a better understanding of our balancing function. Our balancing function then begins with the calibration of the IMU, which is used to determine the vertical position. From there, it reads the gyro and acceleration angles, then calculates to solve for angle offset. If the offset is between 4 and 30 degrees, the robot will move in the direction necessary to balance the robot. But if the robot offset is greater than 30 degrees, the robot will then shut down. If not, the robot will proceed to the RF remote controller receiver function. I will now be passing it off to Eric Lam for obstacle avoidance.
Thank you, Andrew. To begin, the obstacle detection begins after checking whether or not the radio frequency module has received any data. Obstacle detection starts by sending a triggered ultrasonic wave. It then calculates the distance using the time it took for the echoed ultrasonic wave to return to the sensor. If the distance is greater than 38 centimeters, then it will check if every sensor has been triggered. If not every sensor has been triggered, it will send the next ultrasonic detector. Otherwise, if every sensor has been triggered, then it will return to the balancing function. If the distance is less than 38 centimeters, then it will proceed to the obstacle avoidance function. Once obstacle avoidance is completed, it will return to the balancing function. To the right is a flowchart showing the obstacle avoidance. This flowchart is not fully implemented due to the lockdown interrupting all group meetings. When running the obstacle avoidance loop, the robot will not receive any commands from the remote controller until the obstacle avoidance is complete. The robot will default to turning right when an obstacle is detected straight ahead or to the left. However, when an obstacle is detected to the right, it will turn left. The robot then continues to move forward while checking for obstacles either to the right or to the left, then turns back to the starting direction when an obstacle is cleared. I'll now pass it on to Orlando Garcia with the wireless controller.
Thank you, Eric. So last year's team directly wired the controller to the PSOC 6, which is connected to the robot. And one of our main tasks this year was to achieve wireless connection between the robot and a controller. In order to achieve wireless communication between the two microcontrollers, we used two NRF24L01 modules, which are radio frequency modules. And a picture of these modules is shown below. The RFM on the Arduino Uno is the transmitter. The RFM on the PSOC 6 is the receiver. And for the radio frequency modules, a serial peripheral interface, or SPI for short, protocol was used in order to communicate the RFs with one another. The controller consists of the thumbstick, an Arduino Uno, a voltage regulator, and the transmitting module, which makes the controller the transmitting system. And the robot consists of the receiving module, the PSOC 6, the motor drivers, and the stepper motors, which makes this the receiving system. On the right is the flowchart of the Thumbstick Controller, which shows the order that tasks are performed. So first, the thumbstick is moved. Then the transmitter system reads the X and Y axis values from the thumbstick. And then next, the transmitter sends the X and Y magnitudes of velocity to the receiver. And finally, the PSOC6 generates the motor commands sent from the thumbstick. And now Brandon will conclude our presentation.
Thank you, Orlando. Here we are at the implementation phase. The following code has been created, but has not been implemented yet. The obstacle detection for 5 ultrasonic sensors, obstacle avoidance, wireless controller, receiver, and transmitter. The hardware that still needs to be implemented include mounting 2 more ultrasonic sensors onto the robot, attaching the RF module onto the robot, manufacturing 3D printed casing for the wireless controller, and syncing the RF transmitter and receiver. Now for the testing phase, the following tests need to be completed by the future team: wireless controller, transmitter, and receiver, obstacle detection for all sensors concurrently, and obstacle avoidance. Some future improvements the future team can consider: create and implement software to limit time allowed during obstacle avoidance before checking the offset angle for rebalancing. This will keep the robot balancing and from falling over. Model the robot on MATLAB for PID constant improvement. Transfer function for the robot will be provided. And here are our accomplishments and conclusions. The robot is currently balancing properly. When we first got it, it was not moving, so we debugged the code and wiring and found faults in both. When we corrected the PID values, the robot was balancing more precisely. The ultrasonic sensors are successfully and accurately detecting obstacles. Robot can read the distance between the sensor and obstacle, and we subsequently tested 2 ultrasonic sensors, middle right and middle left. Robot compacted by removing the top platform and lower middle platform, and this made the balancing of the robot a lot easier. We added a printed circuit board, which reduced loose wiring and allowed easier access for debugging. Wireless controller has been designed and implemented. First draft code for obstacle detection and obstacle avoidance was generated. And we also generated extensive lessons learned and class 4 documentation for the next team. And that includes our presentation.
Okay, thank you, team. Interesting presentation. We have plenty of time for questions. Let me ask, I want to talk about the PID controller. How did you go about actually improving the balancing? What was the process by which you made it better than it was before?
So at the moment, it is just done by trial and error. So we reduced the constants. At first, it was kind of overshooting it. So we noticed that, and by reducing some of the constants, we were able to do that. But for the future team, we wanted to do it on MATLAB, but due to time constraints, we couldn't do that. We did get the transfer function for the plant, which is a robot. So with that given, hopefully the next team could improve it by modeling it on them.
Okay, so let me explore that a little bit. You said you have the transfer function for the plant, which
Yeah,
is,
there's a robot.
how did you get the transfer function for the plant?
So I think right here. Right here. So basically, there was an online tutorial to do this for inverted pendulum, and we just had to change some of the values for our robot to model it. So one of the things that we looked at was just the force applied by the robot, which is a force that basically anybody could do by pushing the robot over that we have. And then we summed up the forces. We got these equations, and then we were able to get the, well, it's not showing. There was a transfer function in the middle. It's not showing.
Okay, well, keep on that page for a second. I'm really interested in this topic, actually. So, some of those numbers you could calculate and measure. I mean, L and M and
Right.
what G is. Getting numbers like B or I might be more difficult. How How do you go about getting those?
So that's actually where we were saying where we had a time constraint. So we got the transfer function as far as like the equation, but they needed to do the test to find B and I.
So that's work yet to be done?
Yeah, that's work yet to be done.
I see.
Right.
Okay, thank you.
Uh-huh.
Other questions?
Following up on yours a little bit, Mike, I'm actually curious too. What are the ways in which you can measure the moment of inertia of the device? And I'd be curious if there's ways where, you know, are there systems that you can put this on to measure it, or is it kind of fitting, you know, doing some tests and fitting data?
Yeah, I would have. I mean, yeah, I think the way we were looking at it was doing some tests and then fitting the data. Because I know of, I don't think there's any tests or any like specific tests that we could do to get like an exact value. And then we could also run the mass moment of inertia, which I think is based on that too as well.
Gotcha. Yeah, I work on some of the vehicle teams, so we're always interested in what's the moment of inertia, mass moment of inertia of the vehicle is, but we haven't found some great ways to measure it yet.
Yeah, right. That's the best way that I know of, is that just we have to run some tests and then we have to fit the data.
So I'm curious. This is a real. I mean, this is a really interesting topic.
Right.
What sort of instrumentation would you need to put on the robot to collect the data that you need to run those tests and then determine the parameter? Do you feel like the IMU is enough, or do you need more data than that?
We could do it with the IMU. It would depend on how accurate they would want it to be. So just the IMU itself wouldn't be as accurate. They would have to probably run it to see maybe something a little bit more accurate than IMU, maybe a gyroscope that's more fitted for that specific process. But yeah, I think for this case, I think they could do it with just the IMU. It just wouldn't be as accurate as they would want it to be.
Even doing it by hand, you say that you've got it so that it balances reasonably well now?
Yeah, it's just a trial and error thing. So I think we had like a set point to start at. So we had the previous team kind of had it balancing it well enough, and then we just kind of changed up the values to make it balance better. It's just through trial and error.
Okay. Okay. Any other questions? We have plenty of time.
Actually, I have a question.
Go ahead.
My question is, as a group, do you guys ever consider of using like a different sensor to measure like the distance, or do you guys just simply stick with the ultrasonic sensor?
We decided to use the ultrasonic sensors because the previous team also was using them. They seem to be giving like a good distance when calculated as well.
Okay, but you guys like didn't go for any other like sensors, correct?
Correct.
Right.
Okay.
Yeah, I think the ultrasonic sensors worked well with the PSOC from what I saw. So,
Oh, okay.
Because
yeah.
the PSOC is also compatible with like Arduino as well.
Right.
So.
Okay. Okay.
I guess I have one more question, Mike. So I'm curious. It didn't seem like you got a quite chance to test the interaction between the self-balancing and the obstacle avoidance.
Right.
What would you expect to be some of kind of the main issues associated with trying to combine obstacle avoidance and balancing generally, and also like, or if there's anything specifically in your implementation too that you're thinking is going to be tough and you might have to change if you know, after you did some testing?
Right. The main thing is just the robot falling over itself. We did test it with balancing and detecting obstacles at the same time. So we were able to do that, and just that by itself made the robot fall over because it didn't allow enough time between it to balance the robot in between. So the robot tends to unbalance pretty quickly, right? So that's one of the issues. And then one of the things we're looking at for that is since it's going to be avoiding it, we have to make sure that while it is avoiding it, it's also balanced at the same time. So that's the main issue that we're seeing right now that it's going to happen. So So to kind of fix that, we're looking to maybe have a way of limiting the time needed between avoiding obstacles before it has to balance again. And that's probably going to have to be done through tests.
Gotcha.
Right.
Makes sense. Yes, you gotta do some really slow avoidance. You don't want to top of the see it from far away and make subtle adjustments, huh?
Yeah, that's the other thing too. Yeah, we do need to look at the speed of which it's turning the motors, because we don't want it to turn too quickly and then just fall over. Right.
Okay, really cool. I really like your guys' project. Yeah, thanks for the interesting presentation.
Thank you.
Thank you.
Can you hear me?
Yeah.
Steve, go ahead.
This is Belzigi. I'm not on the video. I have a question. In your mass model, what does capital M represent and what does lowercase m represent?
Yeah. So big M is going to be the bottom piece, which is the call it the barrel, I think it's called, and then the little m is going to be the mass of the rod with the bob.
Because if I saw your robot, it's a two-wheel robot, is it not?
Yes, two-wheeled.
So your mass model shows four wheels. So if I hold the wheel fixed, the robot pivots about the axle.
Right. Yeah. So that's where I said we had to change up some of the numbers. So that's where we changed up the mass formula, and then we also had to include the external forces going the other way.
And so you're assuming that the upper part that pivots about the axle is a rigid body. In other words, you don't have any equipment or any wires moving around.
Right.
Okay. Yeah, I mean, if you want to measure for the mass moment of inertia, one way to do it is to make a pendulum out of it. Fix the wheel upside down, put it upside down, and fix the wheel, and swing the robot about the axle and see, measure the period.
Interesting.
So we just flip it around and then put it and then like swing it. We can measure that, the period on that.
I mean, that's in the aerospace industry. Mass moments of inertia are sometimes determined by pendulum methods.
Right. Well, that's interesting.
Thank you for the answer. Very interesting project.
Thank you for your response too. That helped out actually a lot and making some sense out of it.
Okay. Any other questions or comments? All right. Well, thank you very much. Our next presentation is scheduled to begin in about 10 minutes. So we'll wait for that. We don't want to, in case people show up just in the nick of time, we don't want to get ahead of ourselves. So stand by for about 10 minutes, but don't go anywhere. We've got 5 more presentations. The next one is the Kinetic Energy, it's the Baja SAE team, followed by a Kinetic Energy Recovery System team.
Yep.
Okay, welcome back everybody. This is Expo 2020, Cal State LA's first virtual expo. We're on the second presentation of a full plate of presentations today. We'll be going until 6 in this room. Each of the presentations is expected to last about 20 minutes, and then we'll have another 15 minutes or more of questions before we start to prepare for the following presentation. So there should be ample time for questions. You should be thinking about the questions as the students are presenting their material. We have an evaluation form for everybody to fill out when they're done. The Qualtrics link for the evaluation is in the chat. You can click on it from there. If if, or I guess somebody just said, I said, maybe I attached the wrong link. I'll fix that though. If you have difficulty finding that Qualtrics survey, by all means, send me a note and I will send you a link. Okay. Then without any further interruption, let me hand this over to the Baja team for their presentation today.
Great. Thank you, Dr. Bornburn. Thank you everyone for coming to our presentation, and we'll go ahead and get started. So we're Team 81, Baja SAE Data Acquisition and Analysis for Vehicle Design. Our team members include myself, Juan Cortez, Reggie Lau, Alexander Leon, Adam Rico, and Juan Legusamon. Our advisor is Dr. Chris Bachman, and we are sponsored by Capstone Baja SAE. So for our agenda, I'll be covering the project background, vehicle components, and deliverables. Go ahead and move forward. So for project background, Capstone Baja SAE is a student-run team that designs and builds an off-road vehicle that competes against about 100 other universities from across the globe. The main focus of this project is that the forces on the Baja vehicle are relatively unknown to the team, and they're key when designing reliable and lightweight components. As you can see on your right-hand side, there was a front suspension failure during our 2019 California competition. And there was a rear suspension failure during our Rochester competition. And we'll get a little bit more into details on those, but our project will be mostly based on those particular components and the ones around it. So for the vehicle components, we're separating into 3 different sections: front suspension, wheel hubs, and the rear suspension. For the front suspension, we'll be covering the topping arm, bottom arm, and the kingpin. The rear suspension, we'll be talking about the trailing arm. Wheel hubs will be the front and the rear hubs. Now for project deliverables, our aim for this project is to develop instrumentation and a data acquisition system to measure the forces of the front and the rear wheels. Having this data, we'll be able to design and analyze the components for the front suspension, the rear suspension, and the wheel hubs. Now for our requirements, we are required to measure the forces of the front and rear wheels, have a sample rate greater than 10 SPS, have a resolution for the ADC of 16-bit, have a max force pressure of 1,200 pounds by the DAC system, and for our suspension components having a factor of safety greater than 2.5. Now for our team structure. Myself, Juan Cortez, I am taking care of the front suspension, Reggie Lau, rear suspension, Adam Rico will be covering the pressure sensor DAC, Adam Legusamon will be the strain gauge DAC, and Alexander Leon will be covering the wheel hubs. Now I'll pass it off to Juan, where he'll talk about the strain gauge DAC system.
Thank you, Juan. Okay, so I'm going to begin with the car. This is last year's design car, actually. And we are focused on testing the forces that you can see on those red force diagrams there. Now, for the front suspension, it's static for that spindle. So if you see on the right-hand corner for that picture, we can use the strain gauges to detect that deformation of metal. For the rear, though, that spindle is going to be rotating because that's where traction is. So for that reason, we're actually going to be using a pressure sensor for the rear tire. Next slide, please. Now, data acquisition is a system which allows us to measure and store this information, which we can then use for later analysis. The strain gauge is a small sensor which can detect small, minute changes of the metal that it's bonded to. In our case, it's going to be the bending moments. When configured in a half-stone wheat bridge, we are able to detect and measure these volt ranges, which we actually measured to be roughly around the microvolt range. And from there, we can then now exchange and convert this data, or strain gauge data, to pounds forces exerted on the vehicle. Next slide, please. Now, for the data acquisition system, we considered 4 different microcontrollers from the Arduino Nano, the PSOC 5LP, and the Raspberry Pi Zero. We mainly focused and wanted to make sure that this system can be easily configured by future generations of students, and something that they'd be easily be able to recognize and recalibrated if ever needed. We also wanted to consider the size of the unit, so we can have a smaller footprint, the power efficiency, and the adaptability of digital analog to digital converter, or if it has one built in, which in our case, the PSOC 5LP actually met all these requirements, and thus that's what we went for. Next slide, please. Now for the circuit. We ended up using the PSOC 5LP As I mentioned before, now you'll notice that we have two different half-stone bridge. One is going to be measuring the vertical forces that are exerted on the spindle, and the other one's going to be measuring the lateral forces. We use the built-in ADC. It's a delta sigma ADC converter, which we use at 20 bits. All that information is then stored onto the micro SD card, and it's all left in a portable design, which we can then use for later analysis. Next slide, please. Now, we did do the testing on the vehicle. This data was all gathered by one of the Baja SAE members, Ronald Carranza. And here we can see the raw data on the very top, and the bottom is going to be a histogram of that data so that we can make it so it's easily readable. All this data was gathered when we tested at Gorman, and we did it through multiple different runs. This was the best run that we gathered. From here, we were able to calibrate and convert this data into pounds forces exerted on the vehicle, which we noticed that about 99.3% of the force of the longitudinal forces are below 100 pounds force. For the vertical forces, we did expect that to be quite a bit higher, which is roughly about 99.6% are lower than 300 pounds forces. Next slide, please. And now I'll pass it off to the tire pressure jack system, to Adam Rico.
Thank you, Juan. As Juan had mentioned, the strain gauges were required for both front and rear end members. However, the issue we ran into early on was that we could not adapt strain gauges to the rear end members simply because of the members that were in rotation. As a solution, we opted to do tire pressure sensors and adapt that to essentially discover and retrieve the information we were looking for, which was force in this case. Using the pressure function, we solved for force with the assumption that area, in this case, our tire, would be close to constant based on a stiffness study. Next slide, please. The pressure sensor that was used is actually manufactured by Cork. It's called the Tire Whiz. Cork also manufactures power meters for bicycles as well as shock meters. This bicycle tire pressure sensor was adapted for the Baja vehicle. It is a Presta valve, so we did modify the wheels to accommodate both Schrader and Presta valves, which are two different diameters. And we also measured the pressure in kilopascals because we noticed that PSI was not showing us enough change to do anything with the data. So we just had to do a simple conversion later to put it back into PSI, which would be easier to read. The Garmin device that was used, which is also a cycling device, would not only relay the data being measured by the sensors, it would also display it while testing. And it basically would store this data, put it into a cloud account, and we were able to access this data post-testing for analysis. Next slide. We also had to do some form of calibration to ensure the accuracy of this pressure force data that we were retrieving to ensure that we were going to use this properly. We put known loaded forces and would see the change in pressure, and we would do it against a flat surface as well as a pointed surface because there are different surfaces obviously in contact with the tire. We don't know where the force is coming from is obviously the drawback using a tire pressure sensor, but if we can calibrate it, that won't matter. We would know the force that's being experienced no matter the direction of the force. Next slide, please. When pressure testing this, we actually took it to Gorman, California, which was the terrain that was closest to the competition terrain. So there were trails, obstacles that we would encounter, and the type of testing, we would change the driver, we would do hard cornering, and you basically run over any rock gardens, high-speed rollers, or little jumps to gather as much data that you would see in competition as possible. Next slide. The tire pressure analysis, we graphed both the front and rear pressure along with the front and rear forces, and we applied a moving average to kind of see what forces we were experiencing and to also identify what the max force seen in both the front and rear tires were, because we could make the assumption that was the max force being seen on the front and rear suspension members. Next slide, please. So the forces found in the front wheel were anything less than a percentile. We were considering outliers. Therefore, the max force that we were experiencing was 300 pounds on the front end. And for the rear end, the max force we were experiencing was 400 pounds, with a few outliers obviously above that. We used this data as our final data, as what we would see as our worst case scenario for these front and rear end forces. Next slide, please. So to conclude, the strain gauge data and pressure sensor data gave comparable measurements that were basically verifying one another to show the legitimacy of the instrumentation. The max forces seen on the front and rear end respectively were 300 and 400 pounds. And we also make the assumption that the forces that we see on last year's cart, because this was tested on the last year's cart pictured here, were going to be the same seen on the new cart that we had built. And finally, we used these forces in consideration of the front and rear suspension and wheel hub design. I'm going to now hand it off to Juan Cortez, who will now talk about the front suspension.
Great, thank you, Adam. So for our front suspension, we have to look into the previous years, both the bottom arm, top arm, and the kingpin. We noticed that a lot of the strengths came in easy manufacturability and it being lightweight, but some of the downfalls came with the bottom arm and the kingpin, where we actually saw failures during competition and during testing. So knowing this, we'll continue to move forward with our design iterations. So to note before I get into this, suspension geometry and kinematics were considered when designing component dimensions. So on your left-hand side, you have a square tubing construction. On your right-hand side, we have a round tubing construction made up of two different materials, 4130 steel and 6061 T6 aluminum. Last year's previous weight came in at 2.97 pounds. This year's least weight for our iterations came in at 0.98 pounds. Now for the FEA for the bottom arm. Before I start, I do want to mention that the FEA in front of you, what is colored red is in a high stress, and what is more towards a blue hue will be in a lower stress. The load case for these particular components and for the rest of the components will be 300 pounds with a mesh type of a shell mesh and fixtures as a hinge fixed at the suspension points and at the frame side. So based on the FEA results, we noticed that the FEA, the factor of safety shown for previous years came in at around a factor of safety of 5.3 and 5.1, both for the horizontal and the vertical loads. And for our our lightweight component iteration, the 6061 T6 round, it came in at 8.8 for the horizontal load factor of safety and a 5.2 factor of safety for our vertical load. So now moving forward, our top arm design, last year's we focused on a 3/4 inch OD with an 0.65 thickness that came in at 0.42 pounds. This year we wanted to opt into creating a larger diameter, but actually reducing the thickness. We accomplished this by using a design in which we had an inch OD tubing with an 0.35 thickness. This came in at a smaller weight of 0.33 pounds. Now for the top arm design, it's a similar load case scenario as the bottom arm, in which the FEA for the previous arm actually came in at 1.7, and the 1 inch OD with an 0.35 thickness came in at 5.9, which was considerably larger than last year. Now for the kingpin, before we get into the FEA and its analysis, I want to kind of touch on the kingpin sort of uses. So a lot of these brackets on the kingpin are focused on packaging for the brakes, the hubs, and the steering. So with those all taken into consideration, we'll go ahead and move forward with our design. So for our kingpin design, we moved away from a square tubing all the way to a 6061 T6 CNC machined kingpin. We wanted to make sure that our kingpin was easily manufacturable and the dimensions were standardized for CNC machining. Now for the FEA on the kingpin, again, the simulation and the load cases are relatively the same. Last year's square tubing factor of safety came in at 1.5, and this year's 6061 T6 CNC machine came in at 4.9. Now for our suspension trade study. Both the bottom, all three, the bottom A-arm, the top A-arm, and the kingpin, we focused on 4 things: cost, manufacturability, factor of safety, and weight. Now for our bottom A-arm, we decided to go with our 4130 round tubing steel construction. For our top A-arm, we decided to go with the 1-inch OD with an 0.35 thickness. And for our kingpin, we wanted to move towards an aluminum CNC machine build, so we decided to go forward with our 6061 T6 iteration. Now for our manufacturing, a lot of the manufacturing processes that we went through were additive manufacturing, water jetting, welding, and using the CNC machine. When it comes to these manufacturing processes, there are a lot of errors that need to be minimized, and those come into play, or we tried to steer away from those by generating 3D printed mockups to ensure accuracy, and even generating jigs and fixtures for not only the suspension components, but for also the suspension mounting points on the frame. You can see, as a quick example, on your left-hand side picture, a 3D printed model was generated to make sure that the tabs and the fixtures needed for the suspension components were manufactured correctly. So now moving forward, we went from the entire design iteration, from creating a concept and generating a CAD model all the way through to manufacturing and being able to be tested. The front suspension was fully built, mounted, and field tested on the vehicle for 6 hours. We were planning to apply strain gauges on the vehicle to obtain data to validate the front suspension simulations, since the data acquisition system that we used was for previous years. Now, and the test vehicle durability, we're looking at a 30-hour minimum to guarantee the reliability for these particular suspension components. So now I'll pass it off to Reggie Lau, where he'll cover the rear suspension.
Perfect. Thank you, Juan. So as Juan mentioned earlier with the front suspension, we always have to look at the previous year's design first to analyze or to make the new design for this year. As you can see for the photo on the top left, there's a trailing arm and the upright. The upright is essentially the rear suspension's front kingpin. This is where the trailing arm bolts onto the upright and also where the half shaft passes through. So the strengths of this design include that it was easy to assemble, there was alignment adjustability, and there was not a single failure during the 30 hours of testing and at its first competition in Gorman, California. However, as you can see on the photo to the right, later that year, we did compete in Rochester as well. And during the 4-hour endurance race, the trailing arm and shock tab actually sheared off. So for the weaknesses of this design include that it was heavy, manufacturing was extensive and difficult, and also time consuming. Reason being, there was at least 8 different steel bolts being bolted onto the aluminum upright itself. There was a lot of broken tabs in the process, and also the upright had to be remade at least 4 times. Next slide, please. So moving on to this year's trailing arm design, one thing we wanted to make sure was we wanted to get rid of all fasteners. So we wanted to weld the trailing arm directly onto the upright itself. So as you can see here with the 3 different trailing arm designs, they're either utilizing rectangular or round tubing. Reason being is due to its availability and also its cost. So trailing arm 1, again, is at 2.59 pounds, and then trailing arm 2 is at 2.49 pounds. And later on, I'm going to show the FBA on why I chose to optimize trailing arm 3. Which is weighing at 2.9 pounds. Next slide, please. So here, there's FDA for the trailing arm. As Adam mentioned earlier, with the tire pressure DAC system, we were able to obtain the 400-pound vertical forces for the rear end. For this FDA, the shell mesh was applied, and there's also 3 different hinge fixtures. Looking at the trailing arm 1 design, you can see that on the top and the bottom layer of the rectangular tubing, that's where the stress profiles are seen the most. And the reason why you wouldn't want to optimize this design is because there's way too many stress profiles throughout the entire part. So if we were to try to line up this part, the factor of safety was just pretty much reduced from 6.8. So moving on to trailing arm 2, as you can see by the red highlighted circle, that's where the high stress concentration is located. That's essentially where the shock itself is going to be bolted onto. So that's why the gradient on that specific section is so much greater. So that is why we chose to move forward with optimizing this design, because not only were we able to fix that specific stress, critical stress location, but also make it lighter as well. So moving on to trailing arm 3, as you can see by adding 2 gusset plates on both ends, actually increase the factor of safety to 11.6. Next slide, please. So with all the 3 different trailing arm designs and considering the previous trailing arm as well from last year, we put all that into a case study, and then the 5 different categories that we consider were the cost, weight, adjustability, manufacturability, and also factor of safety. As you can see, by weighing all these different designs, the trailing arm 3 was the design that we chose to move forward with. Next slide, please. So now moving on to the manufacturing the trailing arm, the different manufacturing processes that we took were 3D printing, lathing, plasma cutting, tube notching, water jetting, also welding. As Juan mentioned earlier, we will always try to minimize the errors of manufacturing. As you can see in the middle column, we actually flattened the tubes on the CAD model to produce these 1:12 scale paper cutouts for notching. And then on the far right column on the top photo, you can see that we also 3D printed jigs and fixtures. And then we also did some high precision machining. The uprights were actually turned down to tight tolerances to meet the wheel bearing press specifications, as you can see on the bottom left. Next slide, please. So moving forward, very similar to, as Juan mentioned, with the front suspension, the rear suspension was fully built, mounted, and accessed on the vehicle for 6 hours. And our next plan now is to pretty much apply strain gauge on the vehicle to obtain that data to validate that rear suspension simulation. And again, test vehicle durability for 30 hours minimum to guarantee reliability of suspension for a competition. Next slide. And then now I'll be passing on to Alexander Leon for the wheel hubs.
Thank you, Reggie. Like all the other suspension parts, before we got to the designs of the new wheel hubs, we had to look back into last year's designs and the one dated back from 2 years ago. Now, these 2 wheel hubs were made from the same material, aluminum 6061 T6. They both have their strengths, like one being lightweight and the other being more easy to manufacture. However, these 2 are unsatisfactory to the fact that one of them failed at the spoke and cracked, as you can see in the highlighted circle in one of the images, and the other one just simply being too heavy. So the goal for the new wheel hubs was to make the hubs that can withstand the forces that we expect and calculate, and to be light enough for competition. Next slide, please. When making the new designs, we look back at last year's designs due to its simplicity, and we use like FEA with the forces that we calculated, and I'll get to show the FEA analysis about that later. And we looked at the areas that are mostly affected by these forces. So through a process of trial and error, we were able to remove some of the materials within the areas that did not need them and put them into the areas that did need them. For example, we had to increase the rim width to increase the thickness of the spoke. That way it wouldn't crack during competition. Another example is those 3 iterations that you see together on the black box, where we had at the back of the front hub, and we had to remove some material to change the geometry. But by removing some of the material, it caused more stresses. So we had to design a hub that had just enough material to withstand these forces, which led to the final iteration, as you see in the highlighted red box. Next slide, please. Now here we have the FEA analysis for 3 of the forces that we expect to see for design and testing of these hubs. These forces are braking, which occurs when the car moves slightly forward when the driver hits the brakes, impact, which occurs when the wheels hit a bump in the road while it's driving, and cornering, which occurs when the car is making a steady state turn and the load is being transferred from the inside to the outside pair of wheels. Now, looking at these force values that we got, these values are within the expected range that we would see in the front of the front suspension of the car. Of note here, these forces were calculated in the worst case scenario. For example, the braking and cornering were calculated using the high friction factor, coefficient of friction, and the impact were calculated by using 5 Gs instead of the typical 3 Gs. We calculate this with the worst case scenario because even though it's not likely that we might see these forces being high, but if they were to reach this high, this shows that these hubs can withstand such a high forces by giving us these high safety factors, which they should be good for competition. Next slide. So here we have the same FEA analysis done on the rear hubs. Now here we have the forces and stresses being slightly higher than the rear, than the front, as it should, because the rear is more heavier in the back than it is on the front. But since these were calculated in the worst case of scenarios, these rear hubs have a high factor of safety, which should be satisfactory for competition. Next slide. So based on the FEA analysis and using the forces that we calculated and changing the geometry, we were able to come up with a final design for the new rear hubs that would be helpful for competition, as you can see in the two images for both the front and rear hubs. However, once we got to the manufacturing process and started, we were unfortunately unable to finish it due to the COVID-19 pandemic, but hopefully sometime in the future, we are able to finish up these hubs so that we can use them for future competitions and validate our results. Next slide. Now I will pass it off to Juan Cortez to conclude this presentation for us.
Great, thank you, Alex. So now moving forward to our conclusion. We field tested the strain gauge and the tire pressure DAC system to retrieve data and simulate competition environments. The max forces that were seen on both the front and the rear suspension were relatively 300-pound force and 400-pound force. The front and rear suspensions were fully built, mounted, and tested on the vehicle for 6 hours. The hub designs are complete, and like how Alex had mentioned, we'll be going into the manufacturing process soon. Thank you, everyone.
Okay, well, congratulations, team. It was an excellent presentation. Very interesting. We have plenty of time for questions.
Okay, so just round of applause. Thank you very much, Juan, Reggie, Alexander, the other Juan, and Adam. We know this is difficult during these times, and we really appreciate you seeing this through. Did you ever do any sort of a controlled run where you had the vehicle just static, the old vehicle, and measured the forces, and then did a controlled forward acceleration, or even a drop test, or constant radius cornering, and measure the forces from the data acquisition system and see if they make sense?
So we did do a test run on the static force that you would see. We did not do a drop test. We didn't have access to something to drop it, but we did do testing in the parking lot. We would put little obstacles, and essentially like our first semester testing was a lot of running over different obstacles and seeing what those forces were. And yes, to answer your question with the cornering as well, the data was collected for the entire run. So Juan Cortez would do basically laps in the parking lot, and he would corner really hard, and we would see a spike on obviously one tire. We would test because we only had sensors on one side of the cart.
Right.
So we would do a hard left turn and then compare it to a hard right turn. And we were seeing the preliminary data from that and the changes to kind of act as our control, as you had mentioned. We had come to the conclusion that the calibration was going to be a better way to kind of validate the forces, but we did consider that early on in the semester. We just went with a different method to kind of validate those forces seen.
Okay, and just one other quickie is, if you go back to chart 3 or 4, which shows the failure of the suspension member, it's a very long suspension member, and it almost looks like it's a buckling failure as opposed to overstress. And I don't know if SolidWorks can do a buckling analysis. It almost looks like you have this column in buckling, you know, in compression, and it buckled as opposed to material failure. So you might want to leave that as something for future students to consider and think about.
Yeah, SolidWorks does allow us to do a buckling analysis, but it was a little bit difficult, especially with our geometry, to do that. So yeah, it was, we definitely tried doing the buckling analysis, but it just kind of became a bit difficult for us to actually have solid values for us to sort of justify in a way.
Right, buckling is a little bit of artwork to get finite elements to do it. So I'm glad that you considered it. Thank you. Thank you.
Other questions?
I got a question. How did you know what factor of safety was too much, or when you were doing the different iterations? Like, how did you know, for example, a factor of safety of like 3 was better than 2? Like it might be over design. How did you know the difference?
So one of the issues that well, not one of the issues, but one of our requirements were having a higher factor of safety, higher than 2.5. As you can see on and I'm sure you noticed in some of these iterations, like the factor of safety was at, here, let me bring up an example. Like here, the factor of safety for the 41 round tubing was at like 8.6, right? So the aim for this was to being able, once the vehicle was actually built and these control arms were built, our plan was to continue to try and validate and optimize these suspension components. So yeah, you can go as low as 2.5 based on our requirements, but due to time constraints and sort of the situation that we're in, our plan was to optimize these components to reduce its factor of safety. But this is pretty much where we stand now. As far as like why we wanted to go forward with the 2.5 requirements, we just wanted to make sure, especially within Baja and Baja competitions, it's very understandable for you to see forces that are completely unexpected. So we wanted to make sure that we were on top of that. Hope that answers your question.
Yes,
thank you. I had a question following that one actually. So in regards to factor of safety, like let's just say your horizontal load factor of safety is like 14.9. In the event that you guys, hold on, let me formulate this question really quick. Is there, like, if you guys do some testing and you guys see that, you guys' A-arms they held up perfectly fine, is there a chance that you guys will like reduce weight by using like a smaller wall thickness, or like what's the plan for that?
Yeah, so that goes back to sort of Hobby's question, where we wanted to, moving forward, we want to validate these components. So the data acquisition system that Juan and Adam had developed, we were planning to apply those onto the new arms. We'll be able to find different strain and stress readings, different force values that are actually visible within our particular suspension components. And based off of those values, we would continue to move forward and try to optimize these parts. And things like you said, we can maybe reduce the, something similar to maybe like the top A-arm, where we decided to go a larger outer diameter, but our thickness actually reduced. So little things like that, maybe changing the material, overall geometry, and that delves into a huge thing where if you want to change the geometry of a certain component, then on your frame portion of the vehicle, that also has to change.
Thank you.
Yeah.
I have a question. How did you guys look at fatigue, or like your assumptions for fatigue? I mean, maybe I missed it, but if you could elaborate on that, or at least.
Oh, okay. Yeah, we did not go too deep into a fatigue analysis for these components. All the FEA simulations that we do have are all static based simulations.
Is that just because like you guys put priority towards like, okay, if it's gonna break, it'll break because of this rather than fatigue, or?
Right.
Got you. Thanks.
Yeah.
So I have a question on the strain gauge data acquisition DAC system.
Okay.
So how is the strain gauge sensor? How was the selection process for the strain gauge sensor specifically, and like how did you end up with like the specific strain gauge that you end up using?
Okay. For that one, we actually just purchased one of the cheaper sensors that we can find, and ones that can ship to us the fastest. They were, I believe, for micro measurements, they're 350 ohm strain gauge systems. We saw that in their data sheet, they're about a 10 millivolt per volt output of excitation. That seemed, to tell you the truth, there was actually kind of a little bit of trial and error. When we tested these out, we put different loads on metal beam, which actually you see on that picture in the bottom, where it says strain gauge bonded to member. That was one of our test units. And that's the one where we wanted to use a known weight, use different moments to see if we get a proper reading. And we actually noticed that it worked quite well. Another thing too was the size restrictions. The spindle, Juan, can you go up one slide, please?
Sure.
right there, the little kingpin spindle that you notice in the top right-hand corner, it's actually quite small, so we did know we have to use one of the smaller strain gauges. We did see that they have different areas of strain gauges. We did consider too that ideally there's many places where you can put these strain gauges, so we placed it in an area where we know the moment could be the highest. We also, it was kind of all, like I mentioned, a bit of trial and error and just assumptions of where these forces will peak. And we also wanted to use smaller strain gauge systems. That way they can fit properly within that spindle. We don't want to use too big of a strain gauge, because then it could also affect if there's any other force directions that can occur.
Gotcha. And also on page 11, or slide number 11, was there any consideration to, I guess, implement like a sort of amplifier or noise filter system between the Stonebridge circuits to the PSOC 5? Is there like amplifier or noise filter system, or is it just raw data input into the PSOC 5?
In our case, we used raw data. We used about a 60 sample rate, 60 samples per second sample rate. We noticed that gave us fairly good resolution without too much noise, so we didn't really bother in that section. The PSOC 5 LP actually has certain pins. I believe it's one of the 3 pins, 3 point something. Those pins, you can attach an external capacitor to use like a little low pass filter to help improve the noise if needed. Now, I did actually particularly test one on an Arduino setup where we use a Nano. Juan, if you can go up one slide, I want to show you that there. The Nano came quite close to being selected, and in fact, it's still possibly considered, because my idea was using an external, it's a chip called the HX711. It's a 24-bit, so it's a bit higher resolution rather than the 20-bit that we use for the PSOC 5 LP. It's still, with my calculations, it's still very good resolution, so we may not really see too big of a difference there. But now we did, I did go with that HX711 chip, and we did do test the 10 sample. They have a 10 sample per second rate, and they also have an 80 sample per second rate. That one already has a built-in filter system, so that one is one that we're still left to test. I've done just small preliminary tests at home, but we want to do that more for real case scenarios. So once everything clears up, we do want to test that as well and actually compare the two systems, see which one gives us slightly accurate or more accurate results.
I don't think 10 samples per second would be fast enough.
No, we did, when I did test it at home, yeah, I did just put it on a metal bar and I was jumping around. Yeah, right there, we did absolutely notice that some of the peak forces definitely won't be quite close with the 10 sample per second range. I did notice that the noise was definitely greatly improved, but that's one that we don't really quite consider. We're mainly looking at sticking with a 60 sample, 60 SPS, or maybe just moving up to the 80 as well.
And I just want to jump in real quick. Thanks. So it's funny, you guys. We got Ray has tackled this problem, has gotten us close in years past. I want to give credit to Yi. Yi has worked on this system at some point too. So Juan Leguizamon, he joined us about halfway through the year. And Juan, I just want to say you did a great job getting on the team and kind of taking a little bit of what some of the team has already done and like continuing it and learning more on his own. And then we also had Ronald on the team, who should also get credit. But I guess first I just want to say that I'm really impressed with the team. I really enjoyed being a part of this team. I mean, seeing some of the stuff you guys did was crazy, like Reggie 3D printing to jig up his features really precisely. I mean, I never would have thought of some of this stuff. You know, unwrapping the paper, super clever. I'm very impressed that the drive you guys had in December and January, right? I mean, that's something unique that you don't see very often. And I also appreciate you guys. I mean, you see, like, I love to see next year's leader, Javi, already in here giving you guys, talking some smack about how you guys could remove more weight from your car already. So he's already chomping at the bit to make the car faster. But you guys which I think is a testament to you guys and your training of the students, getting the members in the team and stuff, right? So I just want to say I'm really impressed and really enjoyed working with all you guys. So sad to see y'all graduate, but I'd love you have you back anytime and have you teach some of the students what all the stuff you learned.
You might rephrase that, Chris. I don't think you want to say you're sad to see them graduate.
Yeah, maybe yeah. Sad to see them. Sad that I won't see their face around the lab no more. I guess. Happy to see you graduate. That's thanks, Mike.
To what Professor Bachman said, we are happy, but if they have failures in future Bajas, we're going to come and get you.
Okay, we need to move on to the next presentation. Congratulations, guys.
Thank you, everybody.
You did a great job.
Thank you. Appreciate it.
Okay. Set a pretty high bar. We've got about 50 people in the room right now. Our next presentation is the kinetic energy recovery system. Is the entire team here?
Should be. Yes.
Okay, so one member of the team needs to take control of the screen. There's some feedback somewhere.
Probably me. Sorry about that.
I'm going to start muting people until I figure out where that is.
It might be me just because some of my group members were telling me there was issues with my audio. So.
I muted you, Enrique. So Enrique, I think it's you. But obviously you'll need to talk during your part of the presentation.
I'm going first, so I'll mute myself once I'm done with my section.
Okay, very good. Are you guys ready to go then? Okay.
Right. Well, hello everybody. Good afternoon. My name is Enrique Alviar, and then I'm with Team 80 working on the kinetic energy recovery system for bicycles, or as we call it, KERS for short. Team 80 is comprised of Abdullah Gunaim, myself, Guillermo Bellas, Wenchi Guan, Dominic Mamolito, and under the advisement of Ramon Garcia. So the agenda for today's presentation will be covering the background, problem, and objectives of our project, some system level and functional requirements, the theoretical energy consumption of our project, a system overview, design and manufacturing aspects, as well as talk about the mounting device and engagement mechanism, and we'll close off the presentation with some results and conclusions. Some background. Bicycles suffer greatly from energy loss due to frequently stopping in the city. The problem presented to our team 80, was one of kinetic energy losses relating to bicycle riding. While riding the bicycle, the cyclist generates a significant amount of kinetic energy to travel to a destination. Typically, all kinetic energy produced by the rider goes to waste or is lost when we have to come to or are forced to a complete stop. Further resistances, such as air and rolling resistances, as well as losses from drivetrains, aid the loss of kinetic energy even more. Given the amount of kinetic energy that is wasted when coming to a stop, a considerable amount of energy is also required to get the bicycle moving again. Therefore, the task of this project is to find solutions to both of these issues. Proceeding to further define the objective of our project, the scope of this project is to develop a kinetic energy recovery system, which uses regenerative braking to recapture kinetic energy that is potentially lost. The recaptured kinetic energy can then be used to propel the bicycle again and get us moving. In this slide, we outline some functional and performance requirements that we use to design and proceed with our project. We have two basic functional requirements, and they are to store the kinetic energy with regenerative braking, and then the second is to use that same energy to propel the bicycle again. Beneath that are some performance requirements, and they are as listed, and that is to support up to 136 kilograms, or about 300 pounds of the total system weight, overcome a maximum of 5-degree incline, which is your typical stream embankment on the curbside, and be able to achieve a speed of 2.23 meters per second, or roughly 5 miles per hour from the flywheel alone. and also be able to travel a distance of 10 meters, which is a typical distance across the street. And this slide, in this slide, we have some system level requirements. Table 1 in this slide breaks down these system level requirements into design and budget requirements. The total budget allocated to our project was about 300 USD. And then we broke down aspects and components of our project that were greatly affected by this criteria. So for example, we broke it down into the flywheel, the rider, and the bike. These components are then held under the following restrictions. So for the flywheel, for example, the weight must be less than 33 pounds, the thickness less than 2.75 inches, and the diameter under 11 inches. This is to ensure that we can take into account the bicycle that we were donated by Dr. Thorburn. We wanted to have a cost. We didn't want to spend more than $100 on the flywheel itself to ensure that we have money from the budget for other aspects and components of the project. And we wanted to make sure that the flywheel was allocated a decent amount of budget so we can have a decent material that can have a flywheel functioning properly. The rider is also taken into consideration as this, since we don't want the bicycle and the system to be too heavy for the rider to control. Therefore, the rider's weight cannot exceed 245 pounds. The weight of the bicycle cannot exceed 22 pounds, and it's for the same reason as we want the rider to have full control of the bicycle. And then we wanted to allocate no more than $50 of the budget to the bike, so we can have more money for other areas of the project. But as stated earlier, this is circumvented due to the fact that we were donated a bicycle. With the requirements now laid out, I will present to Abdullah to talk about the theoretical energy consumption.
Thank you, Enrique. Here we have the equation used to calculate the kinetic energy going to and from the flywheel, along with the number of rotations and the rotational kinetic energy for the given flywheel diameter. Next slide, please. So assuming 300 pounds weight for the rider and KERS system, we find that the kinetic energy produced to be around 1358 joules. And that when traveling the cruising speed of 10 miles per hour or 4.47 meters per second. Now with assuming 70% efficiency of the entire KERS system and 2% energy loss due to the chain efficiency, the maximum energy we can recover with neglecting the resistances is about 628 joules. And that is enough to get the bike going with a velocity of 3 meters per second or 6.8 miles per hour. This was calculated with the engagement of clutch and flywheel to the energy, and the energy loss during the process was excluded. So we did not account for that. The reason for that being that we were not able to test it, and we could not determine how much energy would have been actually lost. Next slide, please. So there are 3 types of resistances when moving from a stationary point. We have air driver resistance and also climate resistance. We assume atmospheric density, average frontal area of 0.6 meters square, which is the average area when riding in a normal body position. Now the roller coefficient is 0.004, and that is the coefficient when riding on asphalt. Air drag coefficient of 1.15, and finally a maximum street slope of 5 degrees. And here we show the equation we use to calculate each type of resistance. Here we have a plot of all 3 resistances at different speeds, noting that the climate resistance is on the right axis. Since the bike is moving from a stop point, the air drag is minimal, except if we have wind going against the bike. That also applies to the rolling resistance, which depends on the surface area and the tire type. On the other hand, we have the climate resistance, and it's account for the majority of the total. After integration, we find that we need about 36.4 watts to overcome the resistance and reach 3 meters per second. Next slide, please. Here we have a comparison plot showing the energy required on flat ground versus 5 degrees incline, calculated for the same weight assumptions while counting for all the resistances. We find a big difference between the energy required for each, showing that we need a large number of energy to move the bike and the rider up to 5 meters per second. And based on that, we can assume that overcoming the maximum incline might not be possible, especially with 300-pound system or total weight due to the large amount of energy that requires. And now we move to Guillermo to talk about the system overview.
Hello everyone, here I would like to show a simple 2D design that demonstrates the design of the project build. The team made a few modifications to the back wheel and also designed a flywheel system that will store kinetic energy that will later be used by the rider. The way the KERS team approached this problem was to use the energy generated by the rider using the crank gear, which is transfer kinetic energy to the back wheel to move the bicycle forward. Next slide. Since this was the situation, the team decided to have the largest gear possible in the drive due to most of the energy being generated there, and then have a smaller sprocket attached to the axle and the back wheel, which rotates another gear welded to the sprocket. Using the same approach as before, the energy transfer was between the gear drive and the back wheel. A second chain is used to capture a portion of the energy transfer from the back wheel to the clutch. At this point, the clutch will continue rotating until it is engaged by a modified handbrake, which will be discussed further down the presentation. Next slide. As mentioned in the previous slide, the initial position for the clutch will be disengaged. When the clutch engages the flywheel, the energy used to rotate the clutch will slowly transfer to the flywheel until it is disengaged. Once the flywheel begins rotating, the clutch is disengaged and the flywheel begins to rotate freely. When the clutch is engaged again, the energy from the flywheel will be transferred back into the bicycle to help the rider move forward. Next slide. Using SOLIDWORKS motion of analysis simulation system, we're able to see how the system actually works. In this small clip, it demonstrates how the system is supposed to move from disengaged point to engage. When engaging the system, the clutch moves inward slowly towards the stationary flywheel, which then begins to move the flywheel little by little until it picks up speed. This is because we don't want to have the clutch being stopped by friction. Even though the derailleur is not demonstrated here in the clip, the ideal location for it will be somewhere close to the top where the system is located. Next slide. Here we have a preliminary design where the flywheel is going to be located. The idea was to place the system towards the front of the bicycle. This is because we want the rider to have as much space as possible where the rider's legs don't interfere, don't come in contact with the chain going through the bottom. Next slide. We'll now move on to Dominic, who will explain design and manufacturing.
Hello everyone. Here we have a drawing of the flywheel design. On the left side we have our top view, and down on the bottom right we have our section view, which is just if you would draw a horizontal line from the 2A's on the top view and cut the part down the middle there, and that gives you a better idea of how the counterbore and the web was laid out. On this slide, we have a tabulated version of those dimensions and tolerances. As you can see, the most critical dimensions are bolded, and those dimensions were determined by the geometry of the bearing. And as you can see, the tightest tolerance we had to deal with was the counterbar diameter for the bearing, with a +0 and a -7/10,000ths of an inch. And this was to ensure a proper press fit for the bearing. Most of the other dimensions we had a little more flexibility with, and they were basically just determined by the placement on the bike and keeping the design compact, and while still maintaining a high moment of inertia and reaching our target weight. Here we have a picture of the flywheel, the completed version. So basically what we did was we first modeled it in SolidWorks. Next, we water jetted it from a square plate, which was a 1080 hot rolled steel. Then we used a program called MasterCam to determine the tool paths that would be used to achieve our desired shape and geometry. It was machined in a CNC mill, and although some of the surfaces in the middle there may not look smooth, the entire thing is smooth and finished all around. This slide is a simulation from Mastercam, where each one of the tool paths, or each one of the colors, sorry, represents a different tool path. This one right here is one of the more effective. It's called a dynamic roughing tool path. And then what we did was we finished after that, added fillets all around, and then we essentially did the same thing on the back side with the roughing and the finishing, the fillets, and we added counterbores, or sorry, we added chamfers on the counterbore in the middle to make it easier to press fit the bearing in. This is a drawing of the clutch. We have a front view and a top view, and on the front view you can see where we had to cut pockets for, basically what we did was we were using brake pads from another bike to engage the flywheel, so we had to create like recessed pockets, and to do that we had to drill out the corners on the clutch for proper fitment. There's another tabulated version of the dimensions and the tolerances, this time for the clutch. Again, the tight tolerance or the critical tolerance was the one on the through hole, where again, we intended to press fit a bearing. The other dimensions on the clutch were determined by keeping the design lightweight, compact, and effective, which is why we used a large outside diameter. This is a drawing of the shaft design. It was 6 inches long with a 1/2 inch 18 thread on both ends. The idea here was to create a press fit for the side that the flywheel was going to be mounted on to prevent motion, and a slip fit on the side for the clutch to encourage motion. This is just a diagram and tabulated dimensions and tolerances for the bearing. As you can see, the outer diameter of the bearing was the one that affected the flywheel and clutch designs, where the inner diameter of the bearing was what influenced our dimensioning on the shaft design. And now I'll be moving on to Wenji, who will be talking about the mounting device, engagement mechanism, results, and conclusions.
Hello, everyone. We have the KERS system sitting in the middle of the mounting system. We have that ready, but we have to make something to attach KERS to the bike. We have choose a simple and symmetrical designs to put it. The dimension inside is 5 inches wide and 12 inches tall. We have a volunteer to ride on the bike and test out what is the wideness between his two knees. And we have the dimension is approximately 8 inches. We use 5, so there is more tolerance that it doesn't cause any troubles to cause any problems. Also, this mounting system is made of steel 1045 thin square bars, and there is 2 holes on the top and the bottom of the device, which is used for bolting to the bike and prevent wobbling. This design has an estimated weight of 1 pound. Next, please. One of the important setup is the engagement mechanisms. We plan to use the derailleur from the bike to do that. The derailleur will be controlled by a modified handbrake and mounted near the clutch. The initial position is disengaged as the rider is cruising. The rider needs to hold the modified handbrake to engage the clutch to capture energy when coming to a stop. The picture on the right gives an idea of how this process for the engagement actually works. The rider holds the modified handbrake. The derailleur will push the chain and the clutch inward to engage with the flywheel. During this process, energy is going into the flywheel. Then the rider releases the modified handbrake. The energy stored in the flywheel will keep the flywheel spinning. And if the rider wants to use that energy again, he or she can simply press the modified handbrake again to engage. And then this time, the energy in the flywheel will actually coming out and then propel the back wheel and push the riders to go forward. Next, please. And then since we have that mounting system that we have to test it, like what kind of stress and displacements, etc. We use the SolidWorks simulations to do that. The force from the flywheel, the KERS system is acting on the center of the shaft. Looking at the overview picture on the left side, we see that majority of the stress occurs at the center of the shaft. Some stress occurs at the metal bars connecting with the shaft. When we zoom in a little, look at the center, the end point of the shaft has a higher stress value than other places. But we look at the color keys, the maximum stress value, which is 5.59 e to the 2, is well below the yield strain of 7.68 e to the 4 psi. The stress caused by the KERS is still in the elastic regions. Next, please. We are looking at the displacement change. We need to, because since we have the flywheel is press fit and the clutch slip fit to the shaft, we need to know how much it deforms and does that deformation affect the overall settings. Again, the force is applying at the center of the shaft. We can expect the shaft will have a higher displacement deformation in the center. The simulation result shows the center of the shaft does have a higher displacement, but again, looking at the color keys, the maximum value is 8.8 times 10 to the -5 inch. And that displacement is so small that it's probably not gonna change anything. Next, please. As for conclusions, our mounting device can support the 25-pound KERS. Diameter of the flywheel was chosen to be 10 inches with a thickness of 2 inches. The developer was not tested because we were unable to finish the prototype. Based on the calculation, the maximum kinetic energy we can recover is 628 joules, approximately 46% of how much energy we put in. The maximum velocity neglecting resistance is 6.8 miles per hour, equivalent to 3.04 meters per second right after you stop and plan for restart. Overall, the energy efficiency for the KERS system was assumed to be 70% in the calculation. As conclusion that we cannot overcome an incline of 5 degrees when we travel on the street. At the end, we need to use some kind of protections to cover up our KERS system. We think a metal mesh will be good enough to cover it. Next, please. That will be the end of our presentation. Does anybody have questions?
Okay, thank you very much. We do have plenty of time for questions. So just be sure and unmute your microphone before you ask a question. Who'd like to go first?
I've got a question. Where'd the 300-pound rider or 300-pound weight come from? Is that sort of a typical number? It seems kind of large.
Oh, that's something that we designed to put. Originally, we think the bicycle normally weigh like under 20 pounds, yeah. And then we assume our KERS system approximately 25 pounds or unders. So we aim for something high that if a rider weighs 250 pounds, how much energy he can produce and how much energy we can get from it.
Okay.
So that's like the ceiling, the higher end of our calculation. On average, it probably change a little bit on when a normal weight person is performing.
Yeah, to add to that, it was mostly a restriction that we wanted to add, or a requirement that we wanted to place on ourselves in order to make sure that our system and our bicycle and the rider itself can operate the bicycle without exceeding too much of a limit or too much of a weight. It's to ensure that we can ensure that the rider itself can control the bicycle and it's not too much weight for him to lose control and stuff.
Okay. Were there any issues with like center of gravity or balance or anything like that? I know that depends on the kind of bicycle you get, but just kind of curious.
Right. So some of the bicycles that we were donated, they all had different inner frames. Some of them were more like triangular. Some of them were more word? Like trapezoidal, but reversed.
Yeah.
So initially, the one that we were working with was more triangular, which is why we had the KERS system, the flywheel, the clutch, and the mounting device. We had it centered to where it reaches a crankshaft. However, we came up with an issue with the bicycles, and then we had to resort to using a different frame, and that frame was more trapezoidal. So we had to adjust, moving the mounting device and the KERS system a little bit higher, close to the handlebars. And then we did that to ensure that there's more control for the rider as well. Not too much analysis was done into the center of mass and gravity, but we did consider it when we had to rechange our design for that aspect.
Yeah. Okay. Good.
And just add on that real quick. And just the flywheel itself is mounted in the center of the bike, right along the frame, so it's the heaviest component of our system.
Did you consider locating the flywheel anyplace else, or was it always just thought to be there?
No, for the flywheel location, we tried multiple setups. The thing is with going back to where it was having it align with where the gears are at, it really didn't allow for a lot of leg room for the rider. You kind of like you had to open your legs up too wide, and then it seemed very uncomfortable, very awkward. And then we felt that like there were too many issues and too many things to worry about while having it positioned there. Like for example, anything getting caught within the system or the chain, and then allowing enough leg room or proper leg room for the bicycle rider to actually pedal properly. So we played around with it quite a bit. We moved it around here and there. We also took into consideration the weight. Like going back to the previous question, although we didn't really calculate the values for it, we were considering the center of mass a lot, just due to the fact that we don't want the rider leaning too much on one side or leaning too much on the other side, and then we want to be able to have a decent center of balance so that the rider can have as much control as possible.
Okay.
We did kind of think about putting the flywheel with the back wheel, but the issue is that with that it was going to create a lot more modifications required for the bicycle. Where the design we went with, it was more just mounting it to the bike.
Okay. That was actually kind of the location I was wondering about, was coincident with the axial of the back wheel. Okay. Other questions?
I had a quick question. I really liked the project and all the work you put in. I would have loved to see the bike. I'd like your mechanical setup. I'm kind of curious about the mechanical setup. So as you're braking, the flywheel's not moving, right? And your wheel's spinning. And so you start to apply the brake and your flywheel starts to spin up faster and faster, getting closer to the speed of your wheel, right?
Yeah.
But at some point, your flywheel is going to be spinning faster than your rear wheel on your bike. And so you can't actually get all the kinetic energy out of the system, depending on the gearing, because at the low velocities, you would actually be slowing your flywheel down. So was there some thought about that in terms of the gear ratio and like the amount of energy you can get out? So I'd be curious, is that negligible, or is that consequence significant? I'm not sure if you guys, it's not a very well-worded question.
No, I get what you mean. Like basically, when we're going to slow down at some point, we're actually going to be slowing down the flywheel instead of speeding it up anymore, right?
Yeah.
Yeah, that was something we were going to do testing on once we got the whole thing completed, because we couldn't get to that point, we kind of just neglected that.
We did consider it slightly, because we when thinking about how to engage the clutch and the flywheel, we figured that if we try to just snap it on there instantaneously, as opposed to just slowly steering it in, we would get a big problem with that. That would lead to the worst, most likely a complete failure of the system. But we figured that we wanted to be able to move in the clutch as slow as possible. So one of the ways we were thinking about doing that is having a brake handle, with the cable attached, similar to how they're attached for the derailleurs or for the brakes to slowly squeeze in the clutch, so that we don't overcompensate for the greater rotational speed of the flywheel relative to the back wheel. So it was something that was considered, but as Dominic explained, it was something that we're trying to look forward into much further into the development of our project.
Yeah. One more point too is initially we were going to use a 7-to-1 gear ratio where that difference would have been much less, but because I think the issue was finding sprockets that were that small and that large, so we ended up dropping it down to a 3-to-1 where the difference is actually much more significant.
Cool. No, it totally makes sense. And I like your design. It's very intriguing and simple in some ways. And so I'd love to ride the bike and test it out in the future. Maybe next year.
That makes sense.
Yeah, I've got one more question. Well, were there, and speaking of riding the bike, were there any stability issues related to like torque coming from the flywheel, you know, as you either you know, go around a curve or lay the bike down or you know, just ride in anything but a straight line?
That's another thing we never actually got to mount it on the bike and do any test riding or anything with it.
Yeah.
Basically just had all the pieces.
Yeah, I'd be curious to see if there's any kind of residual torques there, or, you know, or does it have to be like perfectly balanced and spinning for the forces to all cancel out? All right, thank you.
Cool if the bike stayed upright by itself because it spun so fast. It's like you have this. It'd be a cool little added feature. You don't even need to put your feet down.
Yeah, that's kind of what I had in mind.
Pretty cool.
Yeah, no, all these things you guys were kind of bringing up, they were initially like at least perceived initially when thinking about the placement of the flywheel itself, because like I said earlier, when we're trying to find the placement for it, we wanted to make sure that the rider has the most control over it. And then we believe that the placement in front, basically at the front end where the handles are, the front end of the part of the trapezoid frame of the bicycle, we believe would give better balance due to the fact to the way a person sits down on the bike. But again, we weren't able to actually mount the system on the bike and test it out.
Cool. Nice work.
Thank you.
Thank you for the question.
Yes, congratulations. It was a great project. Okay, any other questions from the audience? Okay, if not, we'll start to get ready for the next presentation, which should start in about 6 minutes or so. The next presentation is a presentation about gas vapor extraction. When the team is here, somebody can grab a hold of the screen.
Hi there, Professor Thorburn. We the next team. Do we grab the screen right now?
Yeah, you can go ahead and grab the screen.
And do we start at 4 or do we just set up for now?
Yeah, go ahead and set up. We will start at 4 o'clock.
All right.
Okay, we can get started. Welcome to, this is Expo 2020, Cal State LA's first virtual Expo. Thank you for coming today. We're right in the middle of our afternoon session. We have 3 more presentations to go today, and then there's a full slate of presentations both tomorrow afternoon from 2 to 6 and Friday afternoon from 2 to 6. Please come to as many of these as you can and support your fellow students and the program. Our next team. It was sponsored by Sway Features, and they were working on a vapor mitigation extraction system. So without further delay, why don't you guys go ahead and get started?
Thank you for that, Dr. Blumberg. Good afternoon, everybody. Welcome to the Castle Expo 2020. We are at Team 24, Optimization of Vapor Mitigation Extraction Systems. Our capstone coordinators are Dr. Michael Blumberg and Dr. John Bachman. Our sponsors are Sway Features. Our advisor is Sean Kaligi, and our team is comprised of Carlos Mendez, Ulysses Rodriguez, William Jaranto, Jesus Mesta, and Alan Ochoa. Following is the each member's position. A quick history on gas leaks. One recent example of gas leaks would be the Liso Canyon incident in 2015. Now, where this gas leak is of importance was not only was this the largest gas leak in U.S. history, but it also showed the effects that uncontrollable gases can have. And in this case, the gas leak was of great proportion that it displaced an entire community because the members of the community were having effects of dizziness, headaches. Some people were hospitalized. So it just goes to show how effective gas leaks can be if they're not medicated. Now, to the right, you see the 1985 Ross explosion, which shows the deadly consequences of the uncontrollable gas leaks. What happened in this case was that the Ross was built on top of to the designers at that time was they didn't know that there was a methane deposit underground underneath the Ross. So what happened was over time that the methane just seeped into the building and it eventually accumulated inside the building, eventually reaching the auxiliary room. And what happened was in the auxiliary room that the methane caught a spark, and as you can see, there was an explosion from the methane. Now, due to this incident in 1985, the city of Los Angeles began to locate these areas that had high methane concentration. As you can see, this is the city Los Angeles methane zone map. There are two colors, the purple and the yellow. The purple regions are the really concentrated regions of methane, and they are required by law to have methane mitigation systems. And several reasons why these areas have more concentrations of methane could be because they are near oil wells, landfills, or it's just that they are in areas that have just natural deposits of methane. Right now, we'll look into the current application. The current provided to us by Sway Features is a current industry standard of how methane is extracted, where we have a proliferated pipe underground and is installed with vent risers. The proliferated pipe is surrounded by gravel, sand, and then coated with a vapor barrier, and finally with a concrete slab. What this does is it allows for methane to be trapped in an area and just be concentrated in that one area where the proliferated pipe is dug in. And this proliferated pipe in the vents, there's a fan that extracts the methane that enters this proliferated pipe. This is a side view of it. As you can see, the proliferated pipe is surrounded by gravel. What the gravel does, it acts as a chamber for the methane to just enter, and the subgrade and the sand put a lid or enclose the methane just to be in that gravel section. If the methane somehow is able to escape, there is another layer of vapor barrier shown by red, which is comprised of a geotextile fiber that also prevents the methane from escaping. Next, we'll cover the project scope and project objectives. The objectives for this project will be to find and verify theories associated with pressure loss of methane extraction, as well as to optimize the extraction of vapor. We will be verifying these theories and calculating for these losses by doing experimental data and create an Excel file where we will have inputs, and the Excel file will give you the desired outputs for the fan mitigation system that you want to design. Also, we will be dealing with optimizations of the fan selection, the pipe layout, gravel selection, and any sensors or detectors. In the project scope, we will first start with preliminary research, where we will acquire legitimate literature review, and from that literature review, we will take into consideration any calculations that will be relevant to vapor mitigation. After that, we will begin doing some experimentation of qualitative and quantitative data. From that result, we will begin optimization of the system through performance curve and system curves. And finally, we will begin to design the fan design. Next, I'll go into preliminary research.
Okay, now I would like to transition to our first phase, which is conducting research. Next slide. So we started by looking up literature review, but all we found was open loop systems. As you could see to your left, the figure 5 shows a gravel bed river. You could see that the water flows on top of the gravel. And this is called an open loop system because it's driven by atmospheric pressure. This is not ideal for our project because our project is closed loop and it's driven by pressure differentials at the inlet and outlet, shown in figure 6. Next slide. So we took, we decided to do an experiment that accommodates to industry standards and meets our objective. So here's our experimental approach. We still want to keep this T-shape installation so we could have an ideal closed system. So as you could see on figure 7, the top is the industry and then the bottom is what we're trying to assimilate. The things that we're trying, the data that we're trying to obtain is pressure differentials, because that's what drives the head losses, and also the inlet and outlet velocities. And again, we're trying to calculate the head losses of the entire system. Next slide. So I'm going to transition to the design experiment. Next slide. This is the experiment that we came up with. Here are some of the parameters that we have to keep in mind for analyzing pressure drop. As you can see, the pipe, we're going to take in consideration the length and the diameter, and then also the fluid of the smoke that we're going to insert, and then also we're going to consider the volume of the whole system, which is made up of wood and acrylic lid. Next slide. So on the left, you could see already kind of assembled, and it's a cross section. You could obviously see the smoke chamber that we're trying to mimic. This smoke chamber has holes on the bottom, which lets the smoke go in, and then at the top there's holes so the smoke can rise and then go into the perforated pipe. On the right is our first prototype. We did have to put tape to seal some leaks, but there it is. So next slide. So now I'm going to explain our smoke delivery system. So on the bottom, you have 2 smoke machines that go to the inlet valve and then to a T-bar connector, which goes into the bottom T part of the smoke chamber. This is where the smoke is going to accumulate. The valves, we're going to close them so there's no smoke leaking. And then from the smoke chamber, it's going to go into the 3/4 gravel. And again, like Carlos said, we're going to have this be like a reservoir of the smoke. And then in the middle, you could see the perforated pipe go through it. On the left side, you could see that just before it reaches the ball valves, there's a sensor. That's where we're going to measure the pressure. And then there's a ball valve so we could control the smoke. And then at the end, there's an axial fan that we're going to use to extract the smoke. At the other end, it's just open to atmospheric pressure. So next slide. So here we have a SolidWorks simulation. The little spheres, it's the pressure in PSI, pounds per inch, square inch. And then the lines it's the velocity profile in inch per second. So as you could see, we predict that there's going to be accumulation of smoke at the top. And then at the outlet, where you see the little blue spheres, that's where we're going to extract the smoke. So if you, okay, yeah. So that's a little bit about experiment. So next slide.
Okay, so for next slide, it will be my part. I'm going to transition to materials and costs. Next slide, please. Okay, so from here, we can see like from the right table, these are the list of like where we purchase our materials. Most of the material, we acquire them from Home Depot, and most of the stuff that we get from Home Depot are wooden stuff. Wood will be our main material that we use for our frame, for our stand and everything. And from Amazon, we purchase like for our fan. And then from Lowe's, which is like the most important part, is we purchase the clear acrylic sheet. The purpose of using this is like we try to see or like to be able to feel what happened on the sides and on the top side, where it's going to start to accumulate, and we know that the testing are ready to be proceed. Next slide. And then like some of the stuff that we receive are donated and borrowed materials are BMP388, anemometer, foam seal, duct tape, and valves. Next, please. So now I'm going to transition to experiment result, which is going to be divided into two sections, qualitative tests and quantitative tests. The first one will be qualitative tests. In qualitative tests, it's going to be divided into two sessions again. It's going to be in passive tests and force flow test. So the first one will be the passive flow type. What happened with the passive flow type is that we were going to let the smoke accumulate in our experiment table. And once it's accumulate, we're just going to release our hand from the pipe and let the atmospheric pressure do the work and release all of the smoke from our, to extract all of the smoke from our experiment table. From figure 11, you can see that on the left side, once we like start to testing out, we do see like some of the smoke concentration pocket in there. And from the passive flow, what we realize, what we observe as well is that the extraction system like move at a slower pace. And some of the smoke that are in the concentration pocket there, it doesn't really move and we cannot really extract it. And then we're gonna come to force flow type. Okay, so in the force flow type, as you can see in the figure 12, we introduce external force, which is in this case, at that time, we don't really have our fan. So we use a fan blower. In fan blower, it's trying to mimic the characteristic of the fan. And we try to see what will happen with when we introduce this force type. What we really see is that by introducing this force flow, more of the smoke are being extracted. However, we later on try to test by putting a dampener. We just put like our hand on top of one of the outlet in the inlet type valve. What this creates is that it's introducing a pressure differential. And by observing it, it actually extracting more of the smoke, which is at the concentration side. So moving on, once we have done with the qualitative test, we move on to our quantitative setup. In this side, we try to introduce the pressure sensor and the velocity recording. For the pressure sensor, what we use is the BMP388. And then for the velocity recording, as you can see in the figure 14, is the anemometer. Next slide, please. So now after we set up the pressure sensor and the velocity recording, we try to introduce like 3 different layers of gravel into our system. As you can see from figure 15, first we want to see like what will happen if we add 2 inches of gravel, which is on the level A, from the bottom of the T shape of the bar, 2 inches until like the level A. And then for level B will be 2 inches after the level A, and level C will be 2 inches after the level B. And since we already like proven that more of the smoke are being extracted by introducing the force flow, which is the fan blower, now we're introducing our fan. In figure 16, as you can see, is the fan diagram of the team that are using. And next one will be introducing by Jesus.
Okay, so as was said before, the team conducted a few tests to gather data that would represent the amount of head loss in inches of water to a specific flow rate, which can be seen from figure 17, our graph, that was obtained experimentally using the information from table 1. And to find the system head loss, we used the theoretical equation, Bernoulli's equation. And we're going to be using that as a reference for the head loss of the system throughout the testing. Next. Now for the partial gravel, we utilized 66 pounds of gravel for this, and it completely filled the pipe trench, creating a gravel blanket around the perforated pipe. And to obtain the head loss theoretically, we use this equation where it's similar to the head loss of the system, but we just remove that system head loss that we found previously to find the loss of the gravel by itself. Next. Next slide. Oh, wait. This is the full gravel now. So as we can see, similarly, we can get the head loss coming from the gravel, but we'll be using different values for the pressure and the velocities. And again, the experimental prediction of how much head loss will come from a specific flow rate can be seen from figure 19. And we used table 3's information to come up with that. Next. Now for the total fan head required, we used this equation to get it. We just add the system head loss to the respective gravel head loss. And table 4 just shows the main parameters we had to use and we acquired through the testing. And as it can be seen from figure 20, that as we increase gravel weight, we're able to reach a head loss that is higher at a smaller or less flow rate, which indicates to the team that at large amounts of gravel, there will be a significant effect on the flow. Next. And next, we'll be heading into optimization and fan design.
So yeah, I'll be explaining the approaches that we took for optimization and fan design. Next slide, please. So one of our main objectives was to calculate the head loss coming from the gravel for a given system. So we approached this by using the second order trendline equations from our partial gravel and full gravel tests to come up with the gravel losses for the range of volumetric flow rates that we tested at, which is 4 to 14 CFM. We then divided by the weight of gravel used during that test, and we took the average of what we call the gravel loss per pound of gravel used. So next slide, please. So using this model, we wanted to compare the experimental values to the predicted values. So the tables and graphs on the left are for the partial, and the ones on the right are for the full gravel. So as you can see from figures 23 and 24, they're relatively close to each other. Next slide, please. So we also went ahead and predicted the gravel losses for 80, 120, and 200 pounds. And as you can see in figure 25, the higher the CFM, the more significant the gravel losses become. Now, unfortunately, because of the whole COVID-19 situation, we weren't able to verify these predictions by doing tests. So that's probably something that the next year's group can go ahead and try. Next slide, please. Our second main objective was to our second main objective was to optimize the fan design for vapor mitigation purposes. Now, also because of the COVID-19 situation, we were forced to use the experimental values from our fan from the no gravel testing. So we calculated the power going in and the power going out from the fan to calculate the total efficiency. And on figure 28, we extended that trend line to be able to predict the efficiencies at different volumetric flow rates. And on figure 27, you can see from our testing at the highest input power for our fan, the head coming from the fan wasn't enough to meet the requirements for the system. So next slide, please. So we went ahead and created calculators using the total pressure equations and the affinity laws to model fan curves for different parameters. In this case, we used the same diameter. We just changed the input power. So on figure 29, you can see we did fan curves for 3 different input powers, and their efficiencies. Next slide, please. So when it came time to optimize the fan that we were using, we wanted to use the lowest input power possible with the highest efficiency that would give us enough head to satisfy the requirements from the system. So in this case, it ended up being 16 CFM for the fan at 17.3% efficiency. So next slide, please. So here on figure 31, we ended up using running our fan at 0.023 brake horsepower, and the 2 curves met at 2.5 inches of head at 5 CFM. So that's the operating point at which our system will run at. Next slide, please. So due to the combination of time restrictions and the COVID-19 situation, we didn't get into testing for different motors. So we were looking at this motor specifically for its pretty good efficiency, but also it has pretty high RPM for minimum loads, which is what our scenario would look like. And also these types of fans can be easily connected to an Arduino to control the wheel velocity. Next slide, please. So we also wanted to look into blade geometry. We did a lot of research, and in this particular article, it mentioned that more aggressive pitch angles in certain areas of the fan blade create more pressure head, total pressure by sacrificing efficiency. Next slide, please. So going into the conclusion now, next slide. So just a quick summary for our first main objective, which was to calculate the gravel losses. We feel like we kind of met this objective. We were able to create a model using the average gravel loss per pound of gravel, but we weren't able to verify these predictions. And we feel like this model is limited because of the low number of velocities used and the limited CFM that we can predict. Our second objective, which was to optimize the fan design, we don't feel like we met this requirement head on, but we were able to create calculators to predict the fan curves for different parameters. And we were also able to optimize the fan that we were using to meet the requirements of our system curve with the highest efficiency. So next slide, please. That's pretty much it. Thank you for listening. Any questions?
Thank you, team. Interesting project and good presentation. We do have time for questions. So who would like to go first?
I have a question about so you guys had a lot of cases where you measured head loss as a function of flow rate, and you found that the curve was pretty nonlinear. Do you guys, do you think that that data is accurate, and that's just the actual behavior, or do you think maybe there's some kind of error in your measurement of flow rate or pressure drop that's kind of causing that behavior?
So I can answer that question. Looking at the industry system curves and band curves, and also that from the Bernoulli equation, we can see that the losses of a system are squared to the volumetric flow rate. So using a second order equation would make sense in that case.
Why don't you go back to like one of your curve fittings for head loss, like losses versus flow rate, right?
Mm-hmm.
Keep going back before you power stuff. Like maybe like right there, like here, right?
Mm-hmm.
So I think it makes sense that a squared function makes sense, but what I would be like, I'd be curious about what you thought about or what you think about it is, it's a little bit odd that you go from 6 CFM to 7 CFM, and all of a sudden your head loss would go down, right? Like that's a little bit. That's a little bit surprising to me, and so I wonder if you think, is that like really but that's just a curve fit. So it's like, so maybe it's just more important to look at your actual data. But I'm just surprised how flat it gets, below 9. Why isn't it? It seems, it seems like I'd be kind of suspect.
Yeah, I think because we were only able to test at 3 different velocities. I think increasing the the data points would give us like a better insight into that.
Yeah, totally.
Mm-hmm.
Very cool. And then my other question is, do you know like the kind of flow regime that you're in? Is this highly kind of turbulent or laminar? Because you have some areas where it's flowing between gravel, some areas it's in a pipe. Was there some thought about the kind of maybe the different flow regimes you might be in?
The CFMs are pretty low, so we would assume that it was it's pretty turbulent. It'd be we didn't really look into if it was turbulent or laminar, but we kind of just assumed because the CFMs are pretty low and the fluid velocity is pretty low that it'd be turbulent.
Okay, man, no problem. Yeah, I liked all your analysis you're doing and trying to fit stuff. I think I appreciated all the analysis, and I like your mock-up too. I thought you guys did a lot of work on that and got some cool results. So thank you.
Okay. Any other questions? Okay, if not, we've got about 10 minutes between now and the next presentation. But don't go away. This will be a virtual IV blood draw team. In the meantime, you can look on the group chat and find the link to the Qualtrics survey and fill out an evaluation of the presentations that you've been hearing so far today.
Button widgets, and as well as the Save Last button, which actually allows the user to go ahead and export the live data feed. As you can see above from the widget, you see a table that actually incorporates the live feed of not just the time, but also the acceleration values, as well as the angle and the changing thetas, depending on the orientation of the actual accelerometer. Can I get the next slide, please? Okay, so taking in consideration that this was going to be headed off to a different department eventually, we wanted to make this as intuitive possible for a user that wasn't, versed in GUI development or in using, out of the norm GUIs. So we decided to build somewhat of a safeguard. In this case, this GIF is displaying that if you're using the system and you have not selected a COM port or a camera, the system will not run. So this is just something intuitive that allows the user to ensure that the proper hardware as well as the proper software is going to be used. Can I get the next slide, please? Okay, this GIF above is going to demonstrate how the GUI is going to be operated. So first and foremost, you're going to select your communication port as well as your camera. Then you could do a live feed run, which is going to go ahead and accept the data from the accelerometer. To start a new trial run, you could go ahead and press clear. Okay, and then once the data is collected, like for instance, as it's ran, stopped, you have the option to go ahead and save it and then export it as an Excel file, or in this case, a .csv file named test. So this really allows for more arithmetic and more data analysis from the user end, as well as some manipulation in Excel. Can I get the next slide, please? Here's an example of an exported file. The file is a result from the operation of the system displayed in the previous GIF shown. In this format, the user can proceed with, as I said before, any manipulation they want, and they can also pass this data off in, future processing files or processing code that they decide to incorporate within the next parts or other foundational parts of this project. Can I get the next slide, please? Okay, so here's one of the important aspects of our GUI. So we decided to use the Qt library, which allows Python binding units, and in this specific architecture, it runs by signal slot communication. So what that generally means is when we click the widget seen before, for this case, we have the illustration of the Save Last Run As button. So when we click this button sends a signal to the GUI backend, which essentially is just a function. This function then activates our File Explorer dialog, which is your directory whenever you try to save a file. This allows you to go through whatever hard drive, whatever system you're in, select the file and select the name for whatever saving purposes you like. From there, the file is able to be saved and the contents are written into the .csv format. And then once the dialog box closes, that's a signal that the save was a success. Can I get the next slide, please? Okay, now that I went over our simple GUI, I'm gonna go ahead and pass over to Marvin for our conclusion.
Thank you, Nick. I will be summarizing the work done by the group, but before that, I would like to address some of the further developments that could be applied to the project. Next slide, please. Once testing is allowed, calibration of the parameters will be required. It could be done on a dummy arm, and once verified, performed on a live subject. Next slide, please. One of the important things to mention is that once the testing can be done, it can also be used to verify if the microcontroller will be able to process the data fast enough for a real-time application, and whether or not the Logitech camera that we're using will provide enough resolution under different environments. Next slide, please. To conclude, the team was able to quantify the two important parameters for a successful IV insertion. The speed and angle are calculated utilizing the accelerometer, and the data is tabulated on a user-friendly GUI to simplify the analysis of the data. The computer vision would be utilized to verify the data of the accelerometer, and as mentioned earlier, would require further testing to make sure that the data matches the hardware. We believe that the system that we developed would, at a minimum, help a nursing student build confidence with the IV insertion procedure. Thank you.
Okay, thank you, team. Very interesting presentation. We have ample time for questions. If somebody would like to go first. You just need to.
I don't know how the ordering of the questions work, but yeah, great job, team. You couldn't hear my applause I was muted, but great work. I wanted to ask first a sort of a broader question about the metrics that you were recording or measuring. How did you decide on speed and angle of insertion, and could you describe a little bit more about how that would be used by the nursing school or the nurses once you record those?
I guess I can answer that one. So initially we had a lot of other requirements. Because this thing hasn't really been done before, there isn't really objective data for an IV insertion. We kind of started by looking at all the possible metrics we could possibly get. So maybe like we were looking at like getting the force and the angle, the speed, the how much pressure, how much like the depth and stuff. And as we got more and more into the project, and we saw like what our constraints are, because again, our constraints are limited to making something like ideally we would want to make a catheter that has all these cool sensors on it, that's super lightweight, but unfortunately it's not reusable. So we have to come up with like a detachable solution. And as we kind of like fell down the rabbit hole of figuring out what actually does and doesn't work. And we were kind of forced into basically only sticking to speed and angle. And now, like, how does this help? Is again, this metric hasn't been done before. So if you look at like training manuals and guides, the nursing students are trained to, they tell you, I think if I'm not mistaken, the number kind of escapes me right now, but it's like you come in at like 20 to 40 degrees or something like that before you enter the arm. But like, what exactly is that? You know, like if you're a nursing student and you're training for the first time to insert an IV catheter into an arm, like, do you intuitively know what 20 degrees is? And is that really like the best way to do it? And so ideally, you kind of want to just create a platform that can collect any data of any sort and run some trials, so then we can like use that data, maybe look at, like, analyze that data, which this is probably, what I'm describing is a completely different project that we'll have to continue after this hardware is like set up. And basically you can use that data and you can kind of like see if there isn't even a correlation between because what if we find out that, hey, like we find out that if you move at a certain speed, like that tends to actually be more successful than if you just tell people to come in at a certain angle. And then from there, once we have the data, it'd be perfect to like set up like some sort of training apparatus for students to get real practice on. And instead of having to tell them, hey, wait for that pop or wait till you see blood, you know, they can get some practical application and we can kind of reduce the instances of, you know, of bad IV insertions. I don't know about you guys, you ever go to donate blood and you bruise because they messed up? That's kind of like what we're hoping for.
Great, thank you.
Other questions?
Also, could you maybe elaborate a little more on, you mentioned the specs, the performance specs of the accelerometer that you chose, and how you determined that the frequency, for example, which I'm assuming is the sampling frequency, and the sensitivity were sufficient for this application?
Right. Yeah. So for the accelerometer, when we were looking at, we were trying to decide which accelerometer would be best to use, just by looking at how sensitive it is. When we were first looking at what accelerometer to use, we were actually trying to detect force. But as we actually went through some trials, we saw that it wouldn't, the sensitivity that the accelerometer was rated at, it was even too small to, too large to even detect the small amount of force when you're pricking the skin. But when we tested the accelerometer for angle detection, it actually came out pretty decent. Normally, when you kind of like tilt the catheter a certain way, it changes the angle as fast as the eye could see. I know it's not as fast as what we were hoping for, but for the most part, that's what we looked at when we were testing out the accelerometer that we chose. And I do know that the chip that we have, it has the accelerometer and gyroscope included, which will actually bring down the bandwidth that it runs at. So for that case, for the next update, it'd be better if we would include in the PCV chip a accelerometer chip that is pure, a 3-axis accelerometer with the highest frequency available to use in order to try to capture any other data besides angle insertion as the needle's going in.
Thank you.
Okay. Are there any other questions?
I have one for the team. Might be kind of a silly question. You might have even addressed it, but I appreciate all the work you did. You guys going the extra effort to doing the stuff in paint. I actually liked that. I thought it was pretty cool. I was kind of curious. I don't know. My sense is that a lot of the success of someone, being able to draw blood probably has a lot to do with looking at someone's arm and deciding on the location and deciding on the angle and the way to approach the vein. And maybe it has less to do with kind of the relative angle of or the speed of the needle relative to the arm. I mean, would you think, is that really relevant? And would you think it would be worth maybe like having an image of the arm and seeing, what locations they're picking based on what they're seeing on the arm, and and maybe how they're responding to what they're seeing on the arm?
Yeah, I could go ahead and answer that question then. So mainly this might be coming first and foremost from anecdotal experiences. So I do have training as an EMT. So when you are pressing in the actual catheter, acceleration, is kind of correlating to force. So this is very important because you can break through the vein very easily, especially in a rush situation. So beforehand, we were talking about how this is going to be used for a training tool, right, for the health department. And in order to do that, of course, like Omar said before, we can't necessarily teach people, the specific angles, the specific acceleration or anything. It's all about muscle memory. And how you brought up right now, we need that kind of feedback, that direct visual feedback. And although the typical individual wouldn't know the exact metrics, that would be our job, they will know how they're going to react depending on these feedbacks. So in this case, safeguards depending on different boundaries, which would be what we're going to incorporate or hope to incorporate down the line. But to really answer your question, all these do correlate to necessary acts when you're actually doing the demonstration.
Yeah, really cool. I could see it. I could see like a little buzz when they reminds me of like operation when they get outside the guidelines, they get buzzed back into the guidelines to get to
yeah,
it right.
exactly. Yeah,
exactly. Yeah.
It'd be nice to have something that'll detect that they actually puncture through the vein or miss the vein. That way they could know that they just missed it as well.
All right, very, very cool. Thank you, team.
Thank you.
Thank you.
I think you definitely get a lot of nursing students wanting to try out IV insertion if you turned it into operation. I love that game. I had one last quick question about the computer vision. Did you check to see how much the accuracy might improve if you just did a simple improvement with the tape? How the tape was it was taped on, bumpy, it was kind of sticking out. If you just made it nice and symmetric and evenly against around the catheter, do you think that would improve the accuracy, or did you try that out at all? Or
No, you know what's so funny? I actually did, and I had a lot of images where I was at plus or minus 0.15 to like I had it pretty solid, and then I kind of lost some of these files, some of these pictures, and so I was like, oh man, I gotta redo this for the presentation, and so I redid it, and I was like, I got plus or minus 1, okay, let's stick with that. But no, you can definitely because as you smooth it out, it gets a lot better. And the big problem for us was this thing. I don't know if you see my mouse, but because I'm using that open close morphology, you're kind of it's kind of guessing at what the blob is. But again, even with this worst case terrible labeling, I still managed to get, if you look at the needle here and look at what the line is, we're not off by a lot, even when this is imperfect. And another thing too is that, if we were to do this in real life, that testing might not be perfect either, So I just want to showcase that, hey, the signal processing, the image processing that we're doing is there to also kind of take care of any inconsistencies that may occur when you're testing.
Cool, awesome. Yeah, and I'm sure it was good to get some practice with computer vision on more tricky problems. So that's great that you had that example too. Great job again, everybody.
Thanks, Dr. Wan.
Thanks, Dr. Wan.
Thank you, Dr. Wan.
Hey, Manuel, did you have a question? Or? Oh, okay. All right, if there are no further questions, let me congratulate the team, and we will queue up the next team, which is a team with dental implant technology. And that presentation will begin in about 5 minutes.
Thank you, Professor.
Thank you, Professor.
Thank you.
Right, thanks, everyone.
Thank you.
Hello, Professor.
Hi.
We're next, right?
Yes, you are.
Perfect.
Okay, you've grabbed the screen. That's great.
Hello, good afternoon.
Hi.
How are the presentation going so far? Good?
So far, so good. We've set a high bar for you guys. Okay. We'll get started in just a couple more minutes. I want to make sure that people that wanted to come don't find that we started too early and miss out on part of it. I appreciate everybody coming. Please note that we've got a Qualtrics survey for people to fill out. The link to the survey is in the chat room. We welcome your feedback.
Professor, do you see my screen?
I do see your screen, yeah.
Perfect, thank you.
Okay, I think we can get going now. So everybody, welcome to Expo 2020, Cal State LA's first online expo. Thank you for coming to today's session. We're about to start the last paper of today's session. Certainly appreciate everybody sticking around. We've got a pretty good crowd in the audience. And I want to remind you that we have presentations from 2 until 6, both tomorrow and Friday. And I want to encourage you to come to those as well. But without any further delay, by all means, this is the team designing improved dental implants. Go ahead, team. You can start.
Hi everyone, we are team number 20, design and materials for improved dental implants. Team members are Arvin Tarverdi, Michelle, Vertugo, David, and our advisor is Dr. Adel Sharif, and our liaison is Dr. Mir. Our agenda is, I'm gonna go with the background and problems and objectives, and I'm gonna give you guys a brief explanation of the materials. Michelle is gonna go for the design. David is gonna go for the analysis and design, scope of the feature, and again, Michelle is gonna explain you guys the conclusion of our project. This is our project organization. This is our team that we have worked since 2019 from left to right. Again, Dr. Sharif, Michelle, David, myself, and our liaison, Dr. May. So I'm gonna give you guys a brief explanation of the background of this project. The project is about the dental implant. So the dental implant is just permanent tooth restoration. So by all means, when someone is losing a teeth, instead of putting old-fashioned bridge and messing up two dental implant is gonna act like a regular natural teeth. It's gonna give the person ability to eat and speak without getting loose, and also it's gonna help the patient to kind of save the bone, and it's preventing from the bone loss. Problem with this project or problem of these dental implants is kind of in three categories: is biological failure, mechanical failure, and material failure. And as you can see, this is picture of the dental implant. The top one is the screw, bottom one is the abutment, which we're gonna explain a little more. Our objective from 2019 till literally today, it was for 2019, we kind of research on the background like any other project. And we worked on mechanical damping design. By saying it damping, we meant kind of a spring motion, and cementless crown design. On spring 2020, we kind of researching on the material damping as well. So we were looking for a material that can have a spring movement, like micro movement, like our natural teeth. We were gonna do 3D printing, but it got canceled because of the pandemic. And we did the final design. We were gonna build the design on a bigger scale to show it to you guys, but again, we couldn't do that. Dental implant failure. So as I told you earlier, there are three different dental failure. It's a biological failure, so it has nothing to do with the part. It's come from like bad oral hygiene, general health issues, or if someone is smoking, obviously the dental implant's gonna fail. Mechanical failure, it's mainly broken crown, broken abutment, or loose abutment. And material failure, these two are very different. Material failure is, for example, if they use a dental cement that is high soluble with the oral fluid, or dental cement that has a short working time, or for example, abutment that is brittle. So that's gonna go in a category of material failure. We have two main materials that is used in dentistry. It's for implants. It's titanium implants and zirconia implants. They are a little different. Like as a cost, zirconia is more expensive than titanium. But both implants are kind of adapted to human body. They are biocompatible. Strength-wise, titanium is more stronger than zirconia. And safety-wise, both materials are FDA approved. So as a team, after talking to our advisor, we kind of come up with two initial concepts in 2019. It was mechanical damping, as I said, spring effect, and material damping. So we were gonna design a dental implant that has a micro movement like a spring. So it's not solid, so it's not gonna be brittle and it's not gonna break. This is a kind of example of dental cement that is used in industry. There's so many type of dental cements that our team kind of did a lot of research on them to find the best solution. We came with two approaches during our research and designs. We came with abutment mechanical damping and new material to replace current cement. So abutment mechanical damping, we kind of wanted to design an abutment that has that movement, like it's not 100% solid in the mouth. The screw should be solid, like the screw, don't get us wrong, the screw should be very solid when it's inside the bone, but the abutment shouldn't be that solid. That's the big mistake that dentistry is doing even nowadays. And material-wise, again, we were kind of thinking if we can find a material that we can put instead of the current cement that is very solid, how about if we find a material that has a little movement like our natural tooth? So for the material, we researched and we kind of come up with like 6 categories that the material that we're choosing should be, of course, polymer. It should be low cost. Nobody wants to pay more. Should be least soluble with oral fluids. That's one of the problems in the dentistry. And it shouldn't be as strong. So less strength and good sealing ability. We just don't want a material that is not sealing good and easy to remove, because sometimes dentists, they want to remove the crown. So the material that they were choosing, it should be easy to remove. In order to do that, we kind of did a big research for the current cement materials. So there are 5 materials that nowadays, there are so many materials obviously, but there are 5 main materials that dentistry is using. So as a team, we kind of came to the conclusion, let's do the research and find the pros and cons of each material. In that case, we're gonna be able to find a new material. So as you can see there, like resin cement is disadvantage of resin cement is hard to remove. So that's something that dentists, they don't like it. Or for example, glass ionomer, which is called as a GI, one of the advantages, it has a good flow, it's easy of mixing, and it's low cost. It's not that expensive. So that was one of the things that our team did, to just go to the background and see what materials exist so we can come up with a better one. Michelle is going to continue from this slide. Thank you.
Thank you, Arvin. So next slide, please. So I will discuss the different designs for our project, the design for abutment, crown, and screw. And then I'll talk about the final design, and then later on the conclusion. Next slide, please. So before I talk about the designs, I will discuss what periodontal ligament is. Periodontal ligament, or commonly abbreviated as PDL, is a concrete tissue found between the root part of the tooth and the adjacent bone. Its main purpose is to absorb excess pressure from clenching, grinding, and chewing. So when we lose a tooth and replace it with a dental implant, periodontal ligament is absent. Therefore, dental implant is stiff and does not give the natural micro movement that our teeth have. So to make our implant feel like it's a natural teeth, we design an abutment with damping system, where damping means decrease of stiffness to mimic the periodontal ligament. Next slide, please. So for the last semester, we focused mainly on designing abutment with mechanical damping or damping to design approach. And as you can see in the screen, we focus, although the designs with a spiral achieve the damping effect, it also gave us problems such as sharp edges that make the design to fracture easily, and the dreams can easily stick. So to improve that, we come up with 2 final design. Sorry, next slide, please. Which is the mechanical damping and the material damping, where the mechanical damping is that comes with the slot cuts, and then the damping to material is the one with material damping. Next slide, please. So for mechanical damping or damping to design, the slant cuts provide the damping effect that mimics periodontal ligament. It doesn't have any sharp edges, and we put a grooves on the side to make the procedure cementless. However, due to the slant cuts, it is hard to machine. Next slide, please. For material damping, it has the same features as the design, no sharp edges and grooves for the cementless procedure. The cementless procedure by mean that connecting the abutment and the crown. The different part in this design is that there is a gap inside the abutment, as shown in the picture, that a material damping would be inserted, such as the cements that Arvin was mentioned earlier. This cement provide the damping effect, making this design simple and easy to machine. Next slide, please. So for our crown design, there wasn't any big changes. We just added the tongue inside the crown to help us connect abutment cementless. So shown in the far left corner is the bottom part of the crown, where it shows the tongue inside the crown. Next slide, please. So for our screw design, there wasn't any changes at all. This is the like we use our screw dimensions such as diameter as a guide for our whole dental implant. Next slide, please. So overall, this is our dental implant. This is the dental implant that we were picturing that would look like. So on the left side is the abutment with mechanical design. And then on the right side is the abutment with the material damping. Next slide, please. Okay, now so, David will talk about the analysis of the design.
Hello, so I'll be talking about the analysis of the designs. Can you go next, please? So I'll be talking about stress and strain, the finite element analysis that we perform of the designs that we created and the results we obtained from it. And then I'll be finishing with the scope for the future. Next one, please. So first of all, the first thing we have to know, it's in this famous curve, stress versus strain, we see how there is the green line, which is, represents the elastic zone, and then we have the plastic zone. What we want is a material that is tough enough that like covers both parts. It is very elastic and very plastic. In order to achieve this, we have to perform different tests, and then in the lab we have the formulas that we have to apply in order to obtain these results. For the ultimate strength and the yield strength, the values we obtained, it was hard to obtain them from the internet, and for some materials we couldn't find the yield strength, so we approximated those values to similar materials that we found in the website. Next, please. Here are 3 pictures where there are some examples that we obtained from a website. That is the maximum stress, the Young modulus in the bottom left, and in the right we have the maximum strain. As we can see, the materials we talked about is pretty much titanium alloy and zirconia, and those are the ones that have the maximum stress, the maximum Young modulus, and the maximum strain. What we are gonna try to do is find the displacement that we obtain in both designs and see which with displacement we get the higher value compared to the ones that are already created. So next slide, please. So here is an example of different titanium. This is just an example to see how like it's not only about the material, but also how it combines with the materials. As we can see, we have just simple titanium, and that one will have it's less tough, that titanium with tantalum. And then we'll have the highest one, which is the one that is used nowadays, which is the titanium alloy with 6% of aluminum and 4% of vanadium, and that's the very one on the top. And that's what we are trying to mimic with the new designs. However, the materials that we're using could be either the titanium alloy or the zirconia. Next slide, please. So next I'm gonna be talking about finite element analysis. FEA will be the method that we're gonna use to predict how the abutment reacts to forces. We're gonna apply forces on top, and then we're gonna put some fixtures on the bottom to make sure that it doesn't move, because the model is not gonna move. And then we're gonna see how the displacement works. Next slide, please. First of all, what we did is find the modulus of elasticity, the force applied, then the displacement, and finally the stiffness. We find the displacement, as I mentioned before, with a simple formula, and the displacement is equal to force times the length divided by Young modulus times the area. As we can see in the left, we first did it with periodontal ligament. Those results were obtained from the website. It's a self-biological tissue, and the force applied that was in the website was conveniently 500 newtons as well. And as we can see, the displacement was 0.0703. Then we did it with a regular abutment without any slants, and the results obtained, it was 6.93 to the -4. As we can see, it's hard to mimic the periodontal ligament results, even for the ones that are already created. So we're trying to create something that has more displacements than the ones that are created nowadays. And we obtain a kind of good results with abutment with the slants. As we can see, it's 0.0028 8, so it will be like to -3 instead of -4. So those were some promising values. However, for the last 3, as we can see, it says material damping design, and there were 3 different types of materials that we were planning on putting inside. And for those, what we did is we add the displacement we obtained from the material, and we added with the displacements for the regular abutment. As we added both, the difference between the regular abutment went too big, it's still -4. So like with that design, it's hard because we're trying to see how the design works by testing more than by doing hand calculation, because I feel like by hand calculation, we cannot really obtain the results that we want because it's not really accurate as much. Also, I tried to do it through SolidWorks, but through SolidWorks, somehow it asked me a lot of requirements. It not only asked me if I wanted to add a new material, there were some values that I couldn't input, and one of them was yield strength, and I couldn't find the value of yield strength for some materials. So I had to those results by doing hard calculation. Next slide, please. So here's the FEA analysis for the regular abutment. There are no slants in this part, and we can see just the values, the forces applied on top and the fixtures on the bottom. On the top left is the stress, top right is the strain, bottom left is the displacement, and in the bottom right is how it will look the displacement. Is the deformation pretty much. Next slide, please. Here it's just an example of the displacement, just zoom in, and then we probe the top to see what was the difference with the other ones. And as we can see, and as I saw in the table, the result was 6.931 to the -4. That was on the top, and that was the displacement we obtained by applying the force. Next slide, please. This one is FEA analysis abutment with the slants. As we can see, by applying the slants, our displacement will vary a little, and it will go to this where the slant is, and that can create a problem, because if the abutment is gonna break, it will probably break near that. But like as we can see, the yield strength where it's gonna break, it's not gonna be a value that's gonna be near at all, because as we can see in the stress in the top left, we see no orange zones. We just see near the slants, we see some green areas, but other than that, I think it's not gonna break. But I mean, since we couldn't test it, we cannot really know 100% sure, because FEA analysis performs analysis in the future, and so we don't really know if this result is the one that could actually work. Next slide. However, the results obtained with the FEA for displacement were way better than for the regular abutment. It's -3. It's not a huge change, but we can see that it's a change. So we can say that it's actually a better design than the regular abutment without the slants. So we could actually try to build this and see how it will work. Next slide. This one is the one that for the damping design. As I said before, since there is a gap inside, it was hard to perform FEA analysis because we will have to add both displacements for the one with the damping designs and the one without it. But other than that, I feel like this design, if it's built, is gonna obtain better results because it's easy to manufacture than the one with the slants. But it's hard to know if we can get like the great results without actually testing it. Next slide. Here is the displacement. As we can see here, I mean, this design is a little bit bigger. It's not the same one as the regular abutment. So I feel that that's why our value for displacement just for this design is, the displacement is less than the regular abutment. But if we could do both with the same sizes, I think at the end we'll get better results. Next slide. And then the scope for the future will be obviously to build the designs and test which ones work better. We'll be useful to know which material we're gonna use. As the one I mean, I think probably the ionomer, I think, is the best chance to use. If not, we can use another type of cement, and we'll have to do new ways to improve the displacement of the material. However, I feel like with the slants, that's the best we can do. And we will have to find a different way to build it, because I feel like with the slants, we cannot build it in maker space. So we'll have to look in different areas to build that design. But other than that, I feel like we could get something with that design, with both designs, honestly. Next slide. Next is Michelle.
Next slide, please. So for our conclusion, we focus on cementless design when connecting our crown, abutment, and the screw. We completed a design for abutment, mechanical damping, and material damping, and then ran a finite element analysis for both designs. Next slide, please. We would like to acknowledge everyone who helped us in this project, our advisor, Dr. Sharif, our professors, Dr. Bachman and Dr. Torburn, Dr. Raymond as well, and our TA, Edgar, the Makerspace staff, and our liaison, Ramin Mir. Thank you.
Okay, thank you, team. Questions? We have plenty of time for questions. Does anybody want to go first? Well, let me ask, what, if this project were to continue, what would be the first things that you think the next team would need to look at?
For sure will be to test, to try to design the one with the material damping and then test it. And also try to build the one with the slants and test it as well. We were also trying to, with some type of glass, we're trying to create a prototype and see how it will behave under pressure and under force. That was the first thing I think we should try.
Okay.
Yeah, this is Carl Salinas. Yeah, I almost feel like this thing ought to be kind of cleaved along a couple of different fronts, and maybe make one or two other projects with what's here. There's a lot of good meat here that I think could benefit from perhaps a little deeper investigation. So one is just the material science piece. You know, you guys covered at least 3 topics in material science: the adhesives, the material that the anchors are made from. You know, there's the zirconium and the titanium, and then the interface between the attachments. So that's one. The other, again, the FEA. You know, I think there's loads of stuff that can be done there to really understand that question about how you know, a tooth or an implant gets anchored into the jawline and kind of what really happens. And then of course the final one is with the adhesives and, you know, cushioning agents or other materials that might be integrated into that whole design to make it as natural as possible. To me, there's just a lot there, perhaps almost too much to continue on as a single project.
Exactly. Honestly, one of the problems that we've had, from the beginning, it was a group of 4. Then I guess one of the students didn't like the project, so he or she moved on to other project, and we were left with member of 3. But it was a very huge project for 3 persons. Like, as you said, just from the perspective of the material, there is a lot to do a research, and literally we need someone who is good with the polymer chemistry, so we could get a help from that person.
Exactly. I mean, you're hitting it on the head there. I mean, in my own history of having to have some fillings replaced with crowns and things like that, I was surprised that you know, some of the materials that that, you know, that are in use. Not that they're not good, but that they're maybe not as good as what perhaps the industry thinks. I know that in one of my molars, they had to go all the way back just to a, you know, just to a metal you know, cap over it because the zirconium wasn't strong enough. I kept biting down and breaking it. And so, again, also the adhesives were rather brittle. And so they wouldn't go through the heat and cold transitions of, you know, drinking a cold drink or eating hot soup. So there just seems like there's a whole bunch of stuff there that you can investigate.
Yes.
Okay. Other questions?
Yep. This is Adel Sharif, by the way, the advisor for the project, and I want to thank the students. I wanted to make it clear that we did not want to go in too many different ways to make the problem unsolvable. You know, our goal from the beginning was to create a damping effect to prevent the fatigue failure. And this could have been communicated a little better, but that was the thing that we chose a two-pronged approach to solve the problem. One was doing this by a mechanical design that would allow for some elastic deformation so that during the bite, the material won't break, as the previous person mentioned, yeah, when you bite it, if it is stiff, if it doesn't have a give, it breaks very easily. And then the second one was, yeah, cushioning it with some material that provides that dampen effect to prevent either static or fatigue failure during biting. Thank you.
Yeah, I think that message did come through. My comment is really to say that it seems that there are a lot of areas that that are being investigated or perhaps should be investigated in a more kind of maybe parametric way, so that you can gain as much understanding from each option as you possibly can. So one of the things that comes to mind is there a way, you know, you talk about this sort of natural elasticity that teeth have naturally, right? So when you bite down on something,
right,
versus give, how do you measure that? How do you know that you've achieved, you know, that amount of give in what you're going to create?
Yeah, that's the predental ligament Michelle was talking about. Lots of research has been done, and actually the deflection during biting, there's a few microns deflection during biting due to that layer, and that's what we were trying to mimic.
Ah, got it.
Yeah, either through design of the shape, creating some slots that allow for some deformation of the implant, or having a material that material between, let's say, the crown and the abutment, which would allow for some deflection during biting.
Yeah.
By the way, thank you for your comments. Very interesting. Thank you.
Yes, thank you very much.
And thank you for the good work. This is really interesting stuff.
Thank you.
Yeah, it's hard to find something to mimic the periodontal ligament. It's something so unique in our human body that it's hard to mimic that, and that's why like there are so many problems with dental implants, I feel like.
Yeah. Well, it's hard to mimic, but you certainly know when a tooth bottoms out.
Yeah.
Okay. Any other questions? Okay, if not, let me congratulate the team. Job well done.
Thank you.
This will conclude our presentations today. As I mentioned earlier, there is a Qualtrics survey. You can find the link in the chat room. Please fill that out and offer us some feedback. You can fill it out once for each one of the teams. And then remember that tomorrow and Friday from 2 till 6, we'll continue with our Expo 2020 in the electrical and mechanical engineering teams. Thanks everybody for coming.
Thank you.
All right, thanks, Mike.
Thank
See you, everybody.
Bye.
See you, David. Nice job.
Thank you, Professor. Thanks for the feedback this last week.
Yeah, it was very cool. I was impressed. Good work pulling
Yeah.
together some numbers there. It was interesting to see. It was interesting to see some of the numbers, and I wouldn't have guessed that the mechanical one turned out to be better than some of the other ones. It was very cool.
I know. I was kind of surprised myself too, honestly. But the one with it was hard for the one with the material because it was asking me for the geo strength too. Like none of the other materials had geo strength, and that one were asking me for the geo strength, and I couldn't find it. Because I could find other type of values, but geo strength was impossible to find. Yeah, it was tough.
Need for more measurements, man. There's a research study in itself.
Yeah.
The various dental cements.
I'll work on it.
Yeah. You got your claim to fame already.
Thank you very much.
See you,
Okay.
man.
Have a good one.
So long. All right, Chris. We'll catch you later.
Yeah, thanks, Mike. I think it's going well so far. I'm impressed with the attendance and things. Students are going smoothly. I'm good.
Yeah. Okay. Very good. Take care.